Hello guys. So this is our first question of the AC electric circuit analysis, and here we are asked to find the impedances of figure 15.120 in both polar and rectangular forms. Okay, so these impedances are given here. So what is basically the impedance? So recently in our course we have studied the resistance. So resistance is also the impedance where only the resistance or the real quantity is concerned. Similarly, if we have in the circuit which are composed of the inductors or capacitors, okay, so this is the inductor, this is the capacitors. So the reactances which are associated with these elements are represented by XL and XC respectively. Okay, so in any circuit we might have the combination of any of these three elements. So in that case, that resistance or that reactance is basically called the impedance and represented by Z. Okay, so that is basically the impedance, which is basically composed of the real and the complex quantities. Okay, or I can say that real and imaginary quantities. So that would be the impedance. So here in our question A, we are asked to find the or express the impedances in both polar and rectangular form. So initially here in part A we have R 6.8. So as this one is only the real quantity, so here the impedance, let me call it Z1, and Z1 here is only 6.8 ohm. So here this is 6.8 plus J 0, so imaginary quantity here is 0. So that is the rectangular one. Okay, so that is the rectangular representation. Similarly, if I want to represent it in the polar form, what it would be? So it would be like 6.8 whole square plus 0 whole square and square root. So from it I will get also the 6.8, and the angle here will be 0 degrees. Okay, so that is again the 6.8. okay, so that is the solution of my question A. Similarly, in B, what is it asking us to find? So again we are going to express the impedance associated with the circuit in B in polar and rectangular form. So here we are given that the L width or the inductance of the circuit given in B is basically 1.2 Henry. Okay, so from here it is clear that XL is equal to omega L or 2 pi FL, or the value of XC is always equal to 1 over omega C, or that is also the 2 pi F. Okay, so these are the quantities which I will have to find out. Okay, so now here once this 1.2 Henry is concerned, so this is not the impedance here. So in order to find the impedance here, what I have to do, I have to find the value of X of L, and from this equation we have seen that the value of it is 2 pi FL, or in radians, if the frequency is in radians, so what it will be, let me use this one here. Okay, so now here it will be omega L. So in this circuit omega is also given, and that is 377 radians per second. So omega L is the XL, and the value of omega is 377 radians per second, and it is multiplied with L, and the value of L is 1.2. Okay, so multiplying it, let me bring it here. So 377 multiplied by 1.2. So what I will get here, okay, converting it to this one, so I will get here 452.4. okay, so that is basically the inductance here, and that is in ohm. So once the values of the inductive reactance is calculated, so this is basically the imaginary quantity, and here always I have to use the value plus j. Similarly, with x of c, what I have to use? I have to use the value with this denominator as j. Okay. So once this will be used like 1 by j, so I have a knowledge that j is always equal to the 1 over j. Okay, j is always equal to the minus 1 over j, and that is because of that j multiplied by j is always equal to minus 1. Okay, so from it I can see that this will be j 452.4 ohm, or I can also represent it like 0 plus j 452.4. Okay, so that is basically the rectangular form. Okay, similarly here, in order to represent it in the polar form, let me tell you a very simplified version here, and that is let me have it z2, and the value of z2 is 0 plus j 452.4 ohm, and always draw this quantity or this phasor over the complex plane. What it will give me, let me draw it here. When I will draw it over here, I can very easily see that this is the, sorry, this is the imaginary axis, while this was the real axis. So from here we can see that the real quantity here is 0 for all the complex numbers, where only the number is composed of the imaginary quantity. There the real component will be 0, so all the zeros will lie here. Similarly, the value of j52 will lie here because this is the imaginary quantity, so this is the representation of it on the complex plane. Okay, so we can very easily see that the angle it will make with this real axis will be 90 degrees. Okay, so that is basically the scenario where every number which is, let me have this z, and that is jx, so every z which is only composed of the imaginary quantities will have the phase angle equal to 90 degrees. Okay, so you have to remember it that wherever you will get this j, the angle there will be 90 degree. Okay, so the same basically lies here, because now here in this question I have this only j, so here the amplitude will always also be 452.4, and the angle here will be 90 degrees because this is plus j and this is in ohm. Okay, so that is the answer of my question, where this is in polar form and that is basically the rectangular form. Okay, so I hope you have understood what I was talking about. Similarly, let me go to the third one. So in part C here, what we have to find, again we have to find the value of the impedance, and we have to represent it in the form of the rectangular and polar forms. So now here, okay, so this is part C, and in part C I have a frequency of 50 Hertz, while the inductance is of 0.05 Henry. Okay, let me check it again. Okay, so that is 0.05 Henry. Okay, so what we have to do, again we have to find the same values here. So again we can see that XL is equal to the 2 pi FL. So here we know the value of f because it was given here that the frequency or here is basically 50 Hertz, but in the previous question the frequency was basically in radians. So now let me convert it or do it in this manner. So it will be XL is equal to 2 pi and the value of F is 50, while the value of L is 0.05. Okay, so now in order to write it, let me again go to the calculator here. Okay, now 2 multiplied by 50 multiplied by 3.14, that is the value of pi. Okay, and multiplied by 0.0. Okay, so let me print it, and here it is 15.7. Okay, so now let me write here 15.7, and that is XL. And similarly, to represent XL, I have to write J with it. So it is now in ohm, and in rectangular, let me call it Z3, and Z3 is basically 0 plus J 15.7 ohm. Okay, so that is the rectangular representation, while in polar system, as I have earlier discussed, that would be 15.7, and the angle here will be 90 degree because of the plus J and no real quantity here. Okay, so that is again in ohm. Okay, for part D we will come back later on in our next video. So thank you so much, and I will continue this question in our next video. Welcome back, guys. So in previous lecture or in previous video, we have solved the part A, B and C of this question. So today we are going to solve the D, E and F of this question. So let us start here. So now in part D, we have a capacitor of capacitance 10 microfarad, and the frequency given with it is basically in radians. Okay, so let me go down and see that the capacitance here is basically 10 microfarad, and the frequency here is in radians, and that is 100 radians per second. And from it we can very easily see that we have previously, okay, let me now remove it. We have previously seen that the expression for finding the capacitive reactance is basically given here, and by using this expression we will find the value of the capacitive reactance for this capacitor here. Okay, so let me go down. So here we have seen that this is part D. Okay, and the in part D the capacitance is basically the 10 microfarad. Okay, and the frequency, which is basically the radians frequency, is the I think it was the 10 radians per second, or what, 100 radians per second. Okay, so it was basically the 100 radians per second. Okay, so what we have to do, we have to find the impedance, and let me call it Z4, and Z4 is equal to the XC, where XC is the J XC here, and this J XC is the, sorry, not the J XC, but that would be 1 over J omega C. Okay, so writing values here, 1 over J into 10 into 10 raised to power minus 5 into 100. Okay, so 100 is basically the 10 raised to power 2, so 2 multiplied by 10 will be 10 raised to power 3. So here I will get 1 over J into 10 raised to power minus 2, because this 10 raised to power 3 plus minus 5 will be minus 2. So here what I will get, I will get here minus J divided by 10 raised to power minus 2, or minus J 10 raised to power 2, which is the minus J 100 ohm. Okay, so that is basically the answers, and we can also represent it like Z4 is equal to the 0 minus j 100. So that is in the rectangular form here. Similarly, in order to represent it in the polar form, now we can see here that this j is with the negative sign here. So negative sign means that in the z plane or in the complex plane, the vector or the phasor we have will be here. So here it will make this angle with it, which is basically the minus 90 degrees. Okay, so in order to represent the capacitive reactance, what we have to do, if we have any impedance which is solidly composed of the imaginary term in such a way that the j here is negative, so in order to represent it, what we can do, we will have to represent it with the same magnitude, while the angle there was minus of 90 degrees. Okay, so that is the polar representation of the phasor here, okay, or the impedance here. So that is Z4. Similarly, in order to solve the part E of our question, what we have to do, so this is part E of our question. So let me solve it here. So part E, we are given that C is 0.05 microfarad, while the frequency here is 10 kilohertz. Okay, so we can see that now instead of omega, we are given the frequency in hertz. Okay, so what we have to do now here, this is Z5, and that is 1 over j omega c. So 1 over j 2 pi fc. Putting values here, what I will get, so j into 2 pi, and that is 10 to the power 4, because 10 multiplied by 10 to the power 3 is 10 to the power 4, and multiplying here, this is a microfarad. So micro is basically 10 to the power minus 6, 10 to the power minus 6, and these two terms, so 10 to the power minus 8, so 5 into 10 to the power minus 8 here. So now simplifying it again, Z5 equal to the 1 over j, so that 2 multiplied by 5 is 10, okay, multiplied by 10 to the power 4 into 10 to the power minus 8. So this multiplied by this will be 10 to the power 5, sorry, this is 10 to the power minus 8. So what I will get here, that would be 1 over j and 10 to the power minus 3 here. Okay, so now again, okay, so now let me solve it, and by solving it, what I will get here, I will get here minus j 10 to the power 10 to the power plus 3. So that would be the Z5 equal to the j 1000. Okay, so that is the minus j 1000. So in a rectangular system, what it will be, this would be the Z5 equal to the 0 minus j 1000, or Z5 will be equal to, in the polar form, it will be the 1000, and angle would be minus 90 degrees. That is also in ohm, that is also in ohm, and that is the answer of my part E here. Okay, similarly, now the last part here, and here we have to find the value of the impedance when the frequency here is 157 radians per second. So here the impedance Z6 will be equal to the 220 ohm, because the resistor is the linear quantity which doesn't have any association with the frequency. So whatever the frequency will be, the resistance will not be affected by that frequency, okay, because that is the linear element and no frequency will affect over this linear element. Therefore it will be the same as it is, and no J term will appear here, and therefore no phase change will occur when current and voltage will be developed here. So G6 will be 220 ohm, or in the rectangular format it will be 220 plus J0, or it will be 220 and the angle here will be 0 degrees. Okay, so that is the Z6 here as well. Okay, so that is the end of question 1 of our book. So with some more questions I will see you in our upcoming lecture. Thank you so much. Hello guys, so this is the problem number 4 in our book, and today we are going to calculate the total impedance of the circuits in figure 15.123. This is basically the figure where the sub figures are A, B and C, and here we have to express our answers in rectangular and polar forms and draw the impedance diagram. Okay, so in this circuit, first of all, considering the part A of this circuit, so let me have it, let me move down and considering it. Okay, so this first circuit here is basically, let me solve it now, and here we have a resistor and the inductor here, and the inductive reactance is also given here, and that is basically X of L. Okay, so before going to solve this circuit here, let us formulate a general strategy which we are going to follow here. So suppose if we want to calculate the impedance in any circuit, what we have to do, we have to add all the resistances whatever and whichever are here in this circuit, and let me call them I, and I have to sum them together. So let me draw it. So Z equal to the all the resistances. Okay, then what we have to do, we have to look for all the inductances which are available in our circuit, and we have to add it with this one, like plus inserted J, and after it I have to add them, like let me call it K. So in this K, what I have to do, I have to add all the inductances and let me call them K. Okay, so these are all the inductances which I have to add together, and similarly after it minus J and add all the capacitive reactances. Okay, so these are basically L. Okay, so in this strategy at the end we will get the simplified impedance, which will be composed of some component X plus J capital Y, or it can be minus as well. So this will be the cumulative impedance of our circuit. Okay, so we are going to follow the same strategy here. So in our circuit A, what is basically the resistance? So let me call it Z of A, and in Z of A we have only one resistance, so that is basically the R. And what is here we have, here we have basically the inductor. So writing plus J here, and with plus J I have only one inductor, so let me write only one value here. Now writing its values here, so it would be 6.8 plus J, X of L is 8.2. Okay, so that is basically the impedance in rectangular form, and we can very easily calculate it in the form of the polar as well. If we want to represent it in the polar form, what we will do, we will write it like Z and theta here. So Z here, amplitude of Z is basically 6.8 whole square plus 8.2 whole square and square root of it. Similarly, theta is equal to the tangent inverse of y by x, and that is 8.2 whole divided by 6.8. Okay, so in this manner we can calculate the values of Z and theta and put it here, and that would be in the polar format. Okay, so both of the formats. So instead of this we are going to use the calculator trick here, and in calculating it, what we have to do, let me first use this mode here, and in mode I am going to select 2, which is the complex mode. Okay. So, in the complex mode, what I am going to do here, first of all, let me write my values which are given here in the rectangular form. So, 6.8 plus 8.2, and with it I have to write the iota, because this calculator does not have the j term. So, let me write iota here. So, once I have written it, it will be like this one, or I can write it like this. Okay. So, in order to convert it into the polar form, after writing it in the rectangular form, what we have to do, let us press shift here, and here we can see that in 2 it is written the complex here. So, pressing 2 here, we will see that there are basically 4 options, and as we want to convert our rectangular form into the polar form, so it is the third option. So, now pressing 3 here, and you will see that answer will be converted. This arrow means the conversion. So, it will be converted into the polar form. So, now let me press this, and I will see that it will be consist of the value here, which is basically the, let me write here, 10.65, okay, with an angle of 50.33. okay. So, that is basically in ohm. So, this is basically the answer where we have found out the value in the rectangular form and also in the polar form as well. Okay. So, these are basically the two forms, where this is the polar form and this is the rectangular form. Okay. Now, in order to represent them on the impedance diagram, what we can do here, it will be like here, the angle it will make will be 50.33, while the amplitude here will be 10.65. okay. So, that is the answer of part A, where we have calculated all the values which were required. Similarly, in order to solve the part B of our question, let me come over here. Okay. So, again following the same procedure or the same formulation which we have developed here. So, now let me see that how many items do you have. So, I have 2 resistors and one storing element, and that is the capacitor here. So, in order to write the ZA here, what I have to do, I have to add R1 plus R2. okay. And so, as we have the capacitor here, in order to represent the capacitive reactance here, what we have to do, I have to write here minus J, and then I will have to write the X of C. okay. Writing their values, what I will get, sorry, that is basically the ZB. So, ZB is equal to R1, which is 2 ohm plus 10 ohm, and minus J, the value of XC is 6 ohm. okay. So, calculating it, what I will get 12 minus J 6 ohm. okay. So, now this is the impedance in rectangular form, and in order to calculate it in the polar form, let me go back here again, and again writing the values in 12 minus 6 and then writing iota with it. So, this is now in the rectangular form. Again, in order to calculate the values in the polar form, what I have to do, let me press shift here, then this 2 here. So, here I have to convert it in the polar form. So, pressing 3 here, and it will basically convert it into the polar form. I can also do it like this one. So, that is 13.4 and angle is minus 26.5. So, 13.4 and angle is minus 26.5. okay. So, that is also in ohm. So, this one is basically in rectangular form, while this one here is in polar form. Okay. Similarly, what if you want to see that whether these calculated values are correct or not? So, in order to take a look here, so let me find the magnitude here of this quantity. So, let me call it ZB and magnitude here. So, 12 square root 12 square plus minus 6 square and square root here. So, now calculating it over here, what will happen? So, 12 square plus 6 square. Okay. So, the value is 180 and calculating its square root, square root of 180, that would be 13.4, and that is exactly the value which we have calculated for the magnitude. Similarly, in order to find the value of theta, what we have to do? We have to write the tangent inverse of minus 6 over 12, and calculating it, it will also give me minus 26.4 as well. Okay. So, now representing it, let me go down and represent it over the complex plane here. What it will be? It will be the minus 26.5. So, minus 26.5 is basically the clockwise angle. So, that angle would be like somewhere here. Okay. So, and the angle it will make will be 26.5, while the magnitude here will be 13.4. Okay. So, that is the answer of part B. Similarly, in order to calculate the values in part C, here let me call it ZC, and here now let me see that how many resistances, inductors and capacitors do I have here. So, here I have two resistors R1, R2 and two resistor XL1 and XL2 here as well. Okay. So, now let me move on. There are basically two resistors here. So, those are R1 plus R2, and the two inductive reactances are XL1 plus XL2. Okay. Writing their values here, let me see that what are their values. So, R1 is 1 K, R2 is 4 K, similarly XL1 is 3 K and this is 7 K. So, R1 is 1 plus 4 is 5, similarly 3 plus 7 is 10. So, writing it here 5 K plus J 10 K. So, that is basically the total impedance in the circuit given in part C, and this is again in the rectangular form. So, now calculating it in the polar form, let me move again to the calculator. Okay. So, here 5000 plus 10,000 and writing iota with it, it will be like this one. Okay. So, this is my value, and in order to convert it into the polar form, what I have to do? I have to press shift and complex and writing 3 here and equal to, that is 11,180. Okay. So, 11,180 point something, and that something is 0.33 or 34, and the angle it makes with the plane is basically the 63.43, and this is in ohm. Okay. So, now we have our answer. The first one here is basically in the form of the rectangular form, while the second one here is basically in the polar form. Okay. So, that is basically the answer. I hope you have understood all the steps which we have carried out in this problem. Here the formulation which we will be using throughout in this chapter, and this formulation is very important for you to grasp the concepts in impedance calculation. So thank you so much, and I will see you with some more examples in our upcoming videos. Stay tuned, and I will see you soon. Welcome back, guys. So this is the question number 5, and here again we have to calculate the total impedances of the circuits given in 15.124. Here we have to express our answer in the rectangular and polar form, and also draw the impedance diagram. Okay, so basically the circuits here are the what we have recently in our question, but what we have to do here some of the questions are somehow different, and we are going to use the same formulation which we have previously developed in our video. So let us calculate the impedance in our, let me change the color here. Okay, so that is A, and here again ZA is basically the, I have told you that first of all you have to see that how many resistors do I have in the circuit. So here I have only one resistor, similarly one inductors with inductive reactance. What we have to do, I have to put J with it, so writing X of L here, and similarly I also have a capacitor here as well, so writing minus J with the capacitive reactance here. So what will happen, writing it Z of A will be equal to the 3 plus J, X of L is 4, and that is minus J, X of C is 5. Okay, so now writing their values, let me go down here and writing their values, what I will get here, I will get here that the value of Z of A is 3 will remain same here because no real term, no other real term is available here, and also subtracting this minus this 5 from 4, what I will get here minus J 1. Okay, so ultimately I will have Z of A, the value of which is 3 minus J. Okay, so that is the answer in rectangular coordinate system. Converting it into the polar form, what I have to do, I am not going to go to the manual method again and going to do it here. So 3 minus 1 and writing iota with it, that is in the rectangular coordinate system. Converting it into the polar form, let me press shift here, and complex, in complex I have to press 3 and it will give me the answer, and converting into the feasible form I will get 3.16. so that would be 3.16, and the angle here will be minus 18.43. minus 18.43 degrees is the angle associated with it, and that is in ohm. Okay, so from it you can very clearly see that this is basically the rectangular form. Okay, while this one is the polar form, and you can very easily see that as this circuit is composed of the capacitor and inductor as well, but the nature of this circuit will be capacitive nature. Why? Because the negative sign with this imaginary term will basically illustrate us that which type of circuit will we have, and here we have this circuit and the nature of this circuit will be capacitive nature. Okay, because it is there is a negative sign with this J. Okay, similarly in order to calculate the values here in our B circuit here, let me solve it here. So again writing all the values here, so again seeing that how many resistors, capacitors and inductors do I have here. So I have only one resistor, let me call it ZB, so only one resistor. Similarly 2 inductors here, so J XL1 plus XL2, and similarly only one capacitor, so only one capacitive reactance is also here. So writing the capacitive reactance I have to put here minus J, so minus J XC. Writing values here I will get here 1K or 1000 plus J, and value of XL1 is 2K, value of XL2 is 6K, so that would be 8k. Okay, I am simplifying it. So minus j here, and the value of x of c is 4k. Okay, so now again simplifying it, what I will get? I will get here 1k, and subtracting 4k from this 8k, what I will get here? I will get here j 4k. Okay, so now it is basically in the rectangular form. So we can see that here we have different elements. Here we have the inductive reactances, we have the capacitive reactance, and we can very easily see that the nature of this circuit is now inductive because of this positive j in this impedance. Okay, so positive j, the sign of positive is now connected with this j term, and it illustrates that the nature of our circuit is the inductive nature. Similarly, in order to convert it into the polar form, let me go back here again and writing here 1000 plus 4000 and putting iota with it, I will get this one. Okay, now converting it into the polar form, let me put here 2 and now here 3. Okay, so here we will see that this is 4123.10, 4123.10. Okay, and the angle with it is, let me move here further, and 75.96 degrees. Okay, so that is in ohm, and we can clearly see that this is in the polar form. So both of these forms are now calculated. Similarly, in calculating our values for this circuit, here we can very clearly see that the capacitances and inductances are basically given in the form, and we don't have any value for XL and XC. We don't have these values. So first of all, we have to calculate these values, and we know that the value of XL is basically the omega L, which is 2 pi FL, and the value of XC is 1 over omega C, and that is 1 over 2 pi f c. Okay, so let me first calculate the value of omega. So the value of omega is the 2 pi f, and the value of the frequency is also given here, and that is 1 kilohertz. Okay, you can very easily see here that the value of frequency is 1000. So now calculating it, so 1000 multiplied by 2000 multiplied by 2 will be 2000 multiplied by 3.14. okay, so that would be 6280. okay, so that would be omega is 6280 radians per second. So that is the omega, and from it we can very easily calculate our values, which are XL and XC. So here the first XL is here, this is the XL1, this is the XL2, or let me write them in any other color. So writing in them in green. So that is now XL1, that is XL2, and that is XC1. okay, so only one capacitor we have here. So let me calculate them, and let me go down first seeing that what are the values. So the value of L1 is 40 millihenry. So calculating it, now let me calculate it here. So the value of XL1 will be omega is 6280, and that would be multiplied with the L1 here, which is 40 into 10 raised to power minus 3. okay, so now calculating it here, 6280 multiplied by what? Multiplied by 40. okay, so that is this one. Now dividing it over 1000. So what I will get? I will get this one, and this will be 251.2 ohm. So that is basically the XL1. Now calculating the value of XC1, what I will have here, I will have here omega, so 6280 multiplied by the value of the capacitance here, and that is basically 0.1 into 10 to the power minus 6. Okay, so these are the values. So bringing it over here, so this would be 10 to the power 6 divided by this will be 628. Okay, so 10 to the power 6 divided by 628 is how much? 1 2 3 4 5 6 divided by the 628. Here the value will be 1592.4. 1592.4 ohm, and that is basically the value of XC1. Okay, now calculating the value of XL2. So the value of XL2 is again omega L2. So the value of omega is 6280 multiplied by the value which is 200 into 10 to the power minus 6. Sorry, 10 to the power minus 3. Okay, so now 6280 multiplied by 200, okay, and divided by the 1000, what I will get here, 1256. Okay, so here it will be 1256 ohm. So that is the value of XL2. So we have calculated all our values which were needed. The first value is here, which is XL1, because no XL1 was given, and you can see that here it is L1, C and L2. So first of all we have to calculate the reactances, and the first reactance here, second one is XC2, third one is here. We have calculated these values. Okay, and now let me use them in our question here. So in calculating the total impedance here, what we have to do, again the same procedure. So this is part C, and let me call it ZC, and here we have to add the resistor, as we have only one resistor here. Similarly, the plus sign with all the inductive reactances. So we have two inductive reactances which are XL1 plus XL2. Okay, and only one capacitive reactance, and that is XC1. Okay, so now putting their values here, now let me see that what were those values. So the resistance was of 470 ohm. So writing 470 here plus J, the value of XL1 was, it was basically 251.2 ohm. Okay, and the value of XL2 was, how much is it? XL2 was 1256. Okay, we have calculated it here. Okay, this one 1256. Now moving down, 1250. Okay, so now minus J and XCI. So the value of XCI is 1592.4. Okay, 1592.4, and this is for XCI. So 1592.4 and this one. Okay, so now writing values here, 470 plus J, simplifying it, 251.2 and 1256, how much would it be? So 251.2 plus 1256, how much would it be? So it would be 1507.2. 07.2, and subtracting from it this one, 1592 from 0.4. okay. So now we have this quantity which is 1507.2, and we have to subtract from it the 1592.4 to solve or to simplify this equation here. So let me subtract from it 1592.4. okay. So here I will have minus 85.2, so 470, and this is now as minus, so minus j 85.2, yes, 85.2. So this is the value of z of c, and we can very easily see that the dominant term of j here is basically the negative. So the nature of this circuit will be the capacitive. okay. So now converting it into the polar form, what I can see here, that in polar form what we will have, we have 470 minus 85.2 and with it iota. So that is the value, simplifying in this one, and converting it into the polar form, I have to go over this complex here and pressing 3 here. What I will get? I will get 477 again, 477 point what? 477.66. okay, and the angle is minus 10 point how much? Let me look at for it here. So 27.27 degrees. okay. So that is in polar form, and by plotting it over the complex plane, we will see that it will be somehow, let me plot it here. My drawing is not that much good, so plotting it here, I will see that the angle it will make will be the clockwise, and the clockwise angle here. So the values here will be 477.66 and the negative will be 10.27. okay. So why this negative is basically in the fourth quadrant? Because whenever we will have the positive angle, all the terms will be here and the rotation will be the counterclockwise. Similarly, if you want to see, or if you have any negative angle here, how would we represent it? We will basically go clockwise from here. okay. In another form, we can also represent it by subtracting it. If we have any negative angle, we can subtract it from the 360, and the whatever answer we will have, we will plot it in the counter clock as well. So you will see that the same angle we will have while plotting our phasor here, if we are plotting it in the negative form, or we are subtracting it from 360 first and plotting it then. okay. So that is all about it, in which we have seen many applications of the impedance calculations, and I hope it will be enough for you for today. Thank you so much, and I will see you with some more videos. Welcome back, guys. So this is question number 2 of our course, and here we have to find the value of current for the elements given in this figure using the complex algebra. okay. So all the techniques which we have learned so far are going to be used here, and we have to sketch the waveforms for voltage and current on the same set of axes. okay. So here we have this first question, and in this video we are going to discuss this first circuit here in order to formulate the general strategy of solving these type of circuits. okay. So let me go down here. okay. So let me go down and start solving it. So here this is the circuit here, and we have this is, let me have it A, and here the value of resistance is 3 ohm. okay. And the value of voltage which has been developed here across this resistor is 15 sine of omega t plus 10 degrees. Okay, so that is basically the elements and quantities here, and we have to find the unknown quantity, that is the current. Okay, so there again I am going to recall a strategy here, and according to that strategy, with every element, suppose here we have an element here and it can be anything, it has the impedance Z, it has the voltage across it V, and the current across it is I. Okay, so this current is flowing through it, and the voltage which has been developed here is basically this one. Okay, and the impedance it has is basically Z. Okay, and current is this I. So in order to find any one of these quantities, these are basically the three characteristics which are associated with any electric element here. So in order to find any one of the quantity, two other quantities should be known, and by using those two quantities, what I can do, I will use the Ohm's law, which is equal to V is equal to IZ. Okay, so if I want to current here, that would be I equal to V by Z. Okay, after finding the impedance here. So here we can very easily see that the resistance is known. So from the resistance I can very easily find the impedance, and the impedance here, as the only element here is the resistor, which is the real element, so that would be Z is also equal to the resistance, that is 3 ohm. The voltage is also known here. We can see that the overall form of the voltage is known, and this form would be like, okay, so let me plot it in red. This is the pure waveform, and I will call this one as 15 peak. So this will be at minus 15 here. Okay, so that is the amplitude axis, while this is the time axis. So this is the voltage waveform. Here this is the 15 sine of omega t plus 0 degrees, because it is the pure waveform which is starting here from 0. Okay, with the frequency equal to f, such that f is converted into 2 pi f. Okay, so this is the waveform. In order to find this waveform, which is basically 10 degrees from it, what we have to do, I have to plot it here. So I can very easily see that if this is the 90 degree, okay, and this is the 45 degree, then, and the 10 degrees will be somewhere here. Okay, so now let me plot this 10 degree here. Okay, sorry, this will be like here. So this is now starting from 10 degrees, and that is the phase shift or the phase angle it has. So now here this waveform is this is the 15 volts plus 15 volts, and this is the minus 15 volts, and here we have this one as 15 sine of omega t plus 10 degrees. Okay, so that is the overall concept which is related to the sinusoidal waveforms and the phase angles associated with those waveforms as well. Okay, so here we have this sinusoidal waveform, and in order to do this division here, what we know from our previous phasors video is that all the terms here should be in the polar form. Okay, so in order to write the Z in polar form, which is the impedance, we know that this is a real quantity, and therefore the angle associated with it 0 degrees. But what about this voltage? This voltage is neither in rectangular form nor in any other form. This is a pure sinusoidal waveform, and in order to convert it, what we have here, we have basically here this 10 degrees, and this 10 degrees is the angle or the phase angle it has. But what about the amplitude it will have? Will it be 15? No, it cannot be 15, because 15 is the peak value it will have. So in order to convert the peak value into the effective value, what we have to use here, we have to use here the RMS value. And in order to convert any peak value into the RMS, what we have to do, we have to divide it over the square root of 2. Okay. So now writing here this 15 divided by square root of 2. Okay. So now let me go to the calculator and writing 15 divided by square root of 2, what I will get here, I will get here 10.6. okay. So this is 10.6 volt. okay. So now this will be here, this voltage here will be 10.6 and the angle associated with it 10 degrees, and this is in volts. So writing it here, what I will get 10.6 and the angle it will have is 10 degrees. okay. So I think it's now clear. So now solving it, 10.6 divided by 3 and the angles here will be 10 degrees minus 0, because now it will move upward, and we will see that we will get this one. Or we see that in order to build a conceptual overview here, we can also see it in this form, exponential form as well. This is the J0 and this is 10 points, sorry, this is the 3 exponential of J10. okay. So we can very easily see that how this formula will work here. So in order to calculate these things here, what will happen, 10.6 divided by 3, so this is now 3.53 and the angle associated with is 10 degrees, and that is in amperes. okay. So that is the value of watt, this is the value of current, and we will see that according to the calculated value here, the value of the current, okay, which is this one, and the value of the voltage, which is this one. These are basically the two values, and these two values, with these two values the phase angle is equal, and that is 10 degrees. okay. So according to this, the current and voltage are basically in phase when they pass through the resistances. okay. So this is about the voltage and current, and we can very easily see that when these are plotted over the same plot, what we will get. So if we have this axis here, this is the time axis, and I am going to plot the voltage with this blue. okay. So this is 10. okay. So this is what, for the voltage it was 10.6 and also 10.6 with the phase angle of 10 degrees, and the current here is with this one, and the same in phase are basically plotted here. So we will see that the phase and everything was same. So these two are same, but the values here associated with these two are, so let me also plot like this. So this is the current, okay, this is what, this is the voltage, while this one is the current here, and the peak values associated, sorry, these are not the peak values. Let me make a correction here. This 10.6 was basically the RMS value. So here it is basically 15, and this is also 15, and the peak value associated with this one, as the value of the RMS here is 3.53. So this is 3.53, and in order to find the peak value here, what I have to do, I have to multiply it with square root of 2. So multiplying it with square root of 2, what I will get, I will get here 5. okay. So now here this one is 5, while this one is minus 5. okay. So this is the current voltage waveform, and this is all the other things which we have to find out in our part A of this question. So I hope it is clear now. If you have any question, if you have anything to ask, please do write in the comment section, and I will see you with some more examples in our upcoming video. Thank you so much and take care of yourself. Welcome back, guys. So this is the same question number 2 of our book, in which we have to find and sketch the waveforms for V and I on the same set of axes. Okay, so recently we have calculated all these values for part A of our question. So today we are going to discuss part B, where the only element here is the inductor, in which the inductive reactance has been given, and that is 7 ohm. Similarly, the voltage which has been developed across the axle is also given, and that is the 56 sin omega t plus 10 degrees. Okay, so let us proceed further, and here the value of XL is, this is part B, and the value of XL which is given is 7 ohm. Okay, the value of voltage is 56 sin of omega t plus 10 degrees. Okay, so the same question here, in which I have to find the value of I. So in order to find the value of I, what I need, so I is equal to the V divided by Z. Okay, so first of all we have to find the value of Z. Here we can see that the only Z here is the XL, and that is the inductive reactance. Okay, so Z is basically equal to the JXL, because with every inductive reactance you have to write the value of J. So that is the J7, and in polar form it would be, as we have this J. So we have previously discussed that whenever you will have this J in any form, so it will be like 0 plus J7. This is the rectangular form, and in polar form it would be 7 will be the magnitude. So the angle associated with it will be 90 degrees. Okay, so that will be in ohm. Okay, so that is for the impedance Z. Similarly, in order to find the voltage, what we have to do here, we have this peak value. So in order to convert it into the RMS value, what we have to do, we have to divide this 56 over this square root of 2, and the angle is already given here, and that is 10 degrees. So writing it here, okay, and 56 divided by square root of 2 will be equal to 56 divided by square root of 2, that is 39.5. okay, so 39.5, and the angle with it is 10 degrees. So now the value of current, putting values here, let me move down further. Here I will be equal to, putting the value of V, that is 39.5 with the angle of 10 degrees, and the value of Z is also here, and that is 790 degrees. Okay, so here ultimately I will have 39.5 divided by 7, and angles here will be 10 degrees minus 90 degrees. Okay, so 39.5 divided by 7, here divided by 7, what I will have 5.6. so 5.65, and the angle associated will be minus 80 degrees. Okay, so that is the angle of the current, and it will be in amps. So that is the value of current which we have already found out. Okay, in order to plot it, what we have to do, we have this voltage and the current here as well. So we will see that. Let me plot it over here. Let me. Okay, so as this is basically the sine wave, or as this is in polar form, in order to also write it in the sinusoidal way, what I have to do, I have to multiply, this is the RMS value, So in order to convert it into the peak value, I have to multiply it with the square root of 2. So that would be 5.65, and sine of omega t, angle with it is minus 80 degrees. Okay, so it will be 5.65 multiplied by square root of 2, so it will be 8. Okay, so 8 sine of omega t minus 80 degrees. So that is for the current which is flowing through our inductive reactance. Okay, so in order to plot it, what I have to do, let me first plot the voltage here, and the angle with it is 10 degrees. So let me again have it from here. So this is my voltage here, this is the voltage, and the peak value of this voltage is basically 56 volts. Okay, and this voltage is the minus 56 volts. So that is the time axis, this is the amplitude axis, and here we have the voltage here. Okay, similarly, in order to plot the value of current here, the shape will be as that of the sinusoid, but the angle with it is basically minus 80 degrees. Okay, so what is mean by the minus 80 degrees? So here it will be at the 80 degrees, while it will be inverted as that of it. So here this is basically the 90 degrees, so 80 degree will lie somehow here. So it will be like just like here. Okay, such that its peak will be here, and this is just like near to this, and the peak value here will be here, it will be minus 8, while it will be here 8. Okay, so that is basically for the current. So it is somehow higher than that of it, so pardon me for it, but it is for the current. Okay, so this is the plot for the current and voltage over the same axis, and we can very easily and very clearly see that the two plots are 90 degrees away from each other. Okay, and here you will also see that the voltage across the inductor is leading, and that is because the voltage in the inductor basically leads the current, because here you can see that this positive value has been achieved by this voltage curve earlier than that of this current. Okay, so that's why you will also see that the difference between 10 and minus 80 degrees is also 90 degrees. This curve is not that much good, but you should have the idea that how much angle difference should these two will have. Okay, you will also see that it will be like this one. Okay, so let me clear it now. Okay, so this is somehow good, and the idea here will be somehow clear. Okay, so that is all about the part B of our question, and with some more question I will get back to you in our next video. Thank you so much, and I will see you soon. Welcome back, guys. Again, question number 2, and today we are going to solve part C of it. Recently we have covered all the basic steps when the impedance was solely consist of this resistive element, and in part B the impedance was basically the inductive reactance. Today in part C we have the capacitive reactance, which has the value of 100 ohm, and the voltage which has been developed across it is basically 25 sine of omega t minus 20 degrees. Okay, so let me start it, and let me go down, and here in this part C the value of X of C is 100 ohm, and the value of voltage is 25 sine of omega t minus 20 degrees. Okay, so what we have to find out, we have to find out the value of current, and then we have to plot the voltage and current over the same axis. Okay, so let me proceed in it, and here in order to proceed it, what is the procedure here? So again, the formula which we will have will be I is equal to V by Z, where the value of Z is unknown. So here the value of Z is also 1 over j x of c, because x of c is known, and it will be like this one. So here it would be minus j over x of c, because j is equal to, because here I can write that j multiplied by j is equal to minus 1, and therefore j is equal to minus 1 over j. Okay, or I can also write that minus 1 over j, for minus 1 over j, minus j is equal to the 1 over j. Okay, so by using this rule here I have used it, and here minus j over x of c, so that is 100, and here it would be minus j 0.01, and in rectangular form it would be 0 minus j 0.01. Okay, and in polar form it would be, the amplitude will be 0.01, and the angle with it will be, because this is the minus j, so here it would be minus 90 degrees ohm. Okay, so that is the impedance here. What is the value of V? So in order to calculate the value of V, we have this peak value. So in order to convert it into the RMS value, I have to divide it over this square root of 2, and writing the angle here, which is minus 20 degree here, and that is here as well. Okay, so 25 divided by square root of 2 is equal to 25 divided by square root of 2, and that is the 17.67. Okay, so 17.67 or 68, and the angle with it is minus 20 degrees, and this is in volts. Okay, so now using this equation, which is I is equal to V by Z, so putting all the values here, so I is equal to the V by Z's value of V is 17.68, and the angle is minus 20 degrees, while dividing it over this 0.01, and the angle with it is minus 90 degrees. Okay, so now again simplifying it, so 17.68 divided by 0.01. Okay, so that is 1767.8, 1767.8, and the angle here would be minus 20 degrees plus 90 degrees. So ultimately I will get this I, and that is 1767.8, and the angle with it is basically 70 degrees. Okay, so that is in ampere, and that is the answer in polar form. In order to convert it into the sinusoidal form, what I have to do, I have to use the same formula, which is sine of omega t, and with it the angle would be 70 degrees. Okay, but the values here will be 1767.8 multiplied by square root of 2. Okay, so multiplying it with the square root of 2 would be, that is 2500. Okay, so that is the expression for current. Okay, so now in order to plot it, what I have to do, the same procedure again. Let me move down here. Okay, and here again defining the axis. This is the axis here, this is time. Okay, so let me first write the value of current here. So the value of current here, let me write it with this blue, and that would be 70 degrees away. So with 70 degrees away, let me write somewhere here. Okay, so it will be like, okay, and it will be like this one. This is just like 70, and here the amplitude, what will be the value of this amplitude? This is 2500 and this is minus 2500. Okay, similarly, now in order to write the value of minus 20 degrees for the voltage, and for plotting the voltage, what I have to do, I have to use this minus 20 degrees, and minus 20 degrees is basically 360 minus 20 is 340. So it will be somewhat here. Okay, let me use this one. So it will be somewhat here. Yes, and the amplitude here is somehow very low, and that is 25. So writing it like, okay, just like this one. So here the amplitude will be 25, and here it would be, here it would be minus 25. Okay, so this is for the voltage, while this one is for the current, and you can very easily see that the positive voltage is attained by the current earlier than that of the voltage. So therefore in the capacitor, current leads due to the x of c, while V lags. Okay, so that is because of the attainment of the positive value, the current value in the waveform. Okay, similarly, if you want to see the difference or the phase difference between the voltage and the current, you have to write this 70 of the current and then writing minus 20 here. You will see that there will be the phase difference of 90 degrees between the current and voltage in the capacitive circuits as well. But what is the difference between the inductive circuits or the inductive reactances and the capacitive reactances when voltage and current flows? In inductive circuits, voltage leads by 90 degrees from the current, while in the capacitive circuits or in the capacitive reactances, the current leads the voltage 90 degrees. Okay, so that is all about our question, in which we have so far discussed 3 parts of our question. So in order to clarify the conceptual overview of these type of circuits, it was indispensable for me to solve them separately. So I think the concept is now clear, and I will see you with some other questions in our upcoming video. Thank you so much, and I will see you soon. Welcome back, guys. So question number 7 of our book, in which we are asked to find the total impedance in polar form for the circuit, which is given in 15.126. Okay, so what is basically the circuit? Let me move down somehow. So this is the circuit, and in this circuit what we have to do, we have to find out first of all in part A the total impedance. Okay, so let me solve part A here. So in part A, what I have to do, ZT is equal to the total resistance. So only resistance we have this R, so that is the R, and similarly here we have the inductor, so it has the inductive reactance with which I have to write the plus J, so that's why it will be plus J x of L. Okay, so now writing their values, it will be 8 plus J6. So this is now in the rectangular. Now in order to convert it into the polar, what I have to do, let me use the calculator, and here 8 plus 6 iota. Okay, so that is it. And now in order to convert it into the polar form, what I have to do, I have to write it, and it will be 10, and the angle it has is 36.8. So 36.87. So 10, and the angle it has is 36.87 degrees, and that is basically in ohm. Okay, we can also write ohm with it here, but I am writing it here because I have forgot it, and therefore written its angle here as well. Okay, so that is the impedance. Now I have to draw the impedance diagram. So in order to draw the impedance diagram, let me draw it here. Okay, so this is J, this is the positive axis, and what values will I have here? So R is 8 ohm, so 8 ohm is, let me, this is the 8, so this is 8 ohm, and similarly 6J. Okay, so this is the X of L, and X of L is 6. So now it will be like, okay, so let me use this blue color. This is, what is this? This is 8 ohm resistor. This is the X of L. So now the value of resultant is this, and this is Z of t, and the value of Z of t is 10 ohm, while the angle it makes with it is basically 36.87 degrees. Okay, so that is the impedance diagram. Now in part C, find the current I and the voltages VR, VL in phasor form. So in part C here, I have to find out the value of current. I have also found out the value of the total impedance. So therefore finding the current or the total current here is very easy, because this is the total current and the total impedance is also known. So that's why it will be E divided by Z of t. The value of E is known, and that is 100 volts with the angle of 0 degrees. So that is 100, and the angle it has is 0 degrees. Similarly, the Z of t is 10, and the angle it has is 36.87 degrees. Now it will be 100 divided by 10, and the angle it will have will be 0 degrees minus 36.87 degrees. So it will be 10 amps. Okay, I have now written it correctly, and similarly the angle it will have is minus 36.87 degrees. Now this is the current. In order to find the V of R, let me represent them with this green color. So V of R is this current which is flowing through this resistor multiplied by the value of the resistance or the impedance it has. So the current which is flowing through it, as this is basically the series circuit, so from both of these elements the same current has been flowing, and that current is basically I. So therefore I multiplied by R, the value of I is 10, and the angle it has is minus 36.87 degrees. So okay, so multiplying it with the value of R, which is 8. Okay, so that would be 80, and the angle it has is minus 36.87 degrees. Okay, so that is in volts. This is V of R. Now in order to find the V of L, what I have to do, I have to multiply this with JXL, because now it has this value. So the value of I is again known, and that is 10 and minus 36.87 degrees multiplied by the X of L. The value of X of L is 6, but J is available with it, and I have told you that whenever you have any quantity with which J is included, or the imaginary quantity, what we have to do, we have to write the value which is the magnitude, and the angle with it is now 90 degrees. So now the values will be 6 multiplied by 10 is 60 volts. Okay, and the angle it has is 90 minus 36.87 degrees and plus 90 degrees. So how much would it be? 90 minus 36.87, and that is the 53.13 degrees. So as the it is plus here, so that would be 53.13 degrees. Okay, so that is the value of the voltage which is across the inductor. So this is part C, in which we have found out all the values which we have to find out. After it, what we have to do in part D of our question, what is it asking us to do? It is asking us to draw the phasor diagram of the voltages E, VR, VL and the current I. Okay. So in order to draw the phasor diagram, let me move down here. Okay. So now in order to draw it, what we have to do, this is part D. So here let me have this. Okay. So what is E? So E is this voltage. Let me represent is with this blue, all the voltage with this blue. So the first voltage is this T and the angle with it is 0. So that's why this is 100, and let me represent it with this one and writing it like 100 volts. Okay, and this is E with the angle 0. Now I have to represent the value of VR here. So writing the value of VR, and the value of VR is 80 with the angle of minus 36.87 degrees. So as the angle is in minus, so that's why we will move clockwise from here. So it will be somehow here. So it will be like, okay, so this is the VR, and the value it has, amplitude it has is basically this is, let me call it amplitude it has is 80 volts. Okay, so this is V of R. This is V of R. Now after it, I have to represent the value of V of L. So the value of V of L is plus 53.13. So it will somehow lie here. Okay, so this is the magnitude it has is basically how much? 60 volts. Okay, and this is basically V of L. We have written it, and the angle it is making with this is positive 53.13. Okay, and the angle this VR is making is minus 36.87. Okay, so that's why VL and V are 90 degrees apart from each other. So this is the phasor diagrams for the voltages, but now we also have to draw the current here as well. So for drawing current, let me use this green color, and the current here is basically 10 amps, and the angle with it is 36.87. so that is this one. Let me write it like this. Okay, so this is what this is the current. Okay, so in the resistor you may very easily see that the current is in phase with the voltage. So in the resistor, current and voltages are in phase, and you may very easily see from here. But in the inductor, you can see that the voltage is now here, while the current is now 90 degrees away from it. And similarly, we can also see that here the voltage is leading, because it has achieved the positive angle as compared of that of the current. So that's why in these type of circuits where the inductor, the impedance, wherein the impedance, the inductive element is dominant, so these are basically the inductive circuits where the voltage leads while current lags. Okay, so similarly, as you will see that we will also find out the value of the power factor as well. So as the current is lagging here, so therefore power factor will also lag here. Okay, because the power factor of any circuit will be related to the current. Whether the current is lagging or leading, the power factor will also be lagging or leading in that circuit as well. Okay, so that is the phasor diagram of this circuit. Now moving forward here, so we will see that in part E of our question, what we have to do, we have to verify Kirchhoff's law voltage across the closed loop. Okay, so according to the Kirchhoff's law, let me write it here. So according to the Kirchhoff law, E is equal to the VR plus VL. Okay, what is the value of VR? So the value of VR is already known, and that is 80 minus 36.87 degrees, and the value of V of L is how much? That is 60, and the angle it has is 53.13 degrees. Okay, so now in order to do it, what we have to do, let me add them together. So if you are doing it manually, you may basically proceed by using two methods. In first method, you first have to convert these quantities into the rectangular form, then perform the addition here, because for the rectangular quantities, addition and subtraction is the most feasible operation to perform. And after it, once the real and imaginary components has been obtained, you may convert back into the polar form. But in order to use the calculator and for our own convenience, we are going to use our quantities here in this calculator, and the same quantities will be used. So writing here 80, and the angle it has is the minus 36.87, and similarly adding it with the 60, and the angle it has again 53.13. okay, so now adding them together, what will you get? You will get somehow like this one, and that is almost, how much is it? That is 100, and the angle with it is almost 0 degrees. So that is the value of the voltage, which we may see that is also here. So this implies that the KVL is validated. Okay, and the Kirchhoff's voltage law has been proved. Okay, so this is the solution of part E. Similarly, find the average power delivered to this circuit. So in order to find the average power here, what I have to do, this is P, and P is the average power, so EI, and as that is the average power which contains only the real power, so that's why I also have to encounter the angle between the voltage and current, writing their values. So voltage is 100, the current is how much? The current is 10 with the angle of minus 36.87, 10, and cos of minus 36.87, which is as that of the positive one. So writing it here, I will get here 1000 and multiplied by the cos of 36.87. so using it, 1000 multiplied by cos of 36.87, and what I will get here, let me write the negative sign here as well in order to reduce any confusion. So it is now 799.99, which is almost 800. So 800 watt is the power which is the average power. Okay, and now this quantity here, this is the power factor here. So power factor, what is basically the power factor? Power factor is the cos theta, or you can also see that power factor is the value of the real resistance out of the total impedance. Okay, so the ratio of the resistance with the total impedance is basically the power factor, and you may calculate it from this one. So in order to find the average power, you have to multiply with it the power factor as well, which shows you how much energy or how much resistive element is already available in our total impedance. Okay, so that is part F. So after part F, we have to find the power factor of the first sector, indicate whether it is leading or lagging. So again, as we have already found out that, let me call it G. So I have told you that that is cos of theta. So cos of the theta of which the voltage and the total current has. So cos of minus 36.87 degrees. Okay, so let me calculate it. Cos of minus 37.87. So how much is it? That is almost 0.8. Okay, so as the circuit here we have is the inductive, and I have told you that in any inductive circuit the current lags. So therefore this power factor is lagging power factor. Apart from it, as I have told you that power factor is always also equal to the R divided by Z of t. Okay, so the value of R which we have seen here is basically 8 here, because you may see here from this circuit the resistance is 8 ohm, and the value of the total impedance we have calculated, the magnitude it has is basically 10 ohm. Okay, so now writing it here, I will get this 10, and from it I will again get this 0.8, and due to the nature of the circuit, that is lagging. Okay, so from these two methods we can calculate the power factor here. Okay, similarly in part H of our question, we are asked to find the sinusoidal expression for the voltages and currents if the frequency is 60 hertz. So I am going to write the sinusoidal expressions for the E, V R and V of L. So for writing them, what I have to do, that is part H, and here the frequency is 60 hertz. Okay, so therefore the angular frequency will be 2 pi f. Okay, writing their values. So 2 pi 60, and that would be 120 pi radian per second. So that is the frequency. In order to find the value of the total voltage here, so the value of the total voltage here was 100 degrees, where this voltage is basically the RMS value, while this is the phase angle. So therefore in order to write them in the form of the sinusoidal wave, what I have to do, I should have the peak values. So converting the RMS value into the peak values, what I have to do, I have to multiply with a square root of 2, and that is the RMS value it has, and after it the sine of omega t plus theta. So omega is already known, and that is 120 pi of t, and the angle it has is 0 degrees. So that's it. Similarly, the value of V of R, was how much? So the value of V of R was 80 minus 36.87. So the same procedure here, 80 minus 36.87. So the same procedure here, same rule here, 2 multiplied by 80 and sine of 120 pi t, and the angle it has is 36.87 degrees. Similarly, V of L, the value of V of L was how much? Let me see here, that was 60 volts and the angle with it was 53.13. So writing it here, 60 volt, 53.13 degrees. So the same procedure here, square root of 260 and sine of 120 pi t, and the angle is 53.13 degrees. Okay, so this is about all the voltages. Similarly, in order to convert the current into the sinusoidal form, what I have to do, I have to write the value of current. So the value of current is how much? I have calculated it here as well, and that is 10 amperes minus 36.87 degrees. 10 amperes and minus 36.87 degrees. Okay, now the same rule which we have seen here, that is square root of 2 multiplied by 10, and that is sine of 120 pi t, and the phase angle it has is 36.87 degrees. Okay, so that is for the current. Here we have seen the current in the phasor form, and here the sinusoidal form as well. Okay, so what is the last part? So in last part of it, I have to plot the waveforms for the voltage and currents on the same axis. So again I have to plot these values over the same axis. So let me represent this voltage with this red color, this V of R with blue color, this with the green color, and the last one here, this current with the black color. Okay, so let me plot it here. Let me have it here. This is, let me call time axis. So first of all, let me plot the voltage here. So for plotting the voltage, the angle is 0 degrees, phase angle is 0 degrees. So it is now very easy for me to plot them. Okay, so that is the value of the voltage. So the peak value it has is this square root of 2 and 100, and this is the negative peak value, which is minus square root of 100. Okay, so now after it we have V of R, the angle it has is minus 36.87. so that's why this is representation with this one. This 36 somehow lie here. Okay, and as this one is basically the negative one, so 360 degrees minus 36.87 is almost, I think, 323.2 something. Okay, so that is somehow here. Okay, so that's why this will start from here. Okay, so phase angle is here and it will start from here. So this will be like this one. Okay, so this will be like this one. So this is phase it has, and the amplitude it will have will be square root of 2 into 80s. Okay, so that is for the V of R. Similarly, for V of L, the angle is 53.13 degrees, and I am going to represent it with this one. So 53.13 degrees lies somehow here. Okay, this is the 90 degree, this is 45, so it almost lie here. So let me write it like this one. So this is will be like this one. Okay, so I think it here I have made some mistake. So here it will be, you may grasp that how it would look like, such that these two will be 90 degrees apart from each other. So that is what this is V of L, this is V of R. Okay, so these are the voltages, and the amplitude it has is basically this one, sorry, with this green. Okay, so that is the amplitude. Now the last one here is the current, which is in phase with the voltage across resistor here. So again, now this is this one, so again this will be like, now it will be like this one, because this one will be like this. Okay, so that is the value of the current here. And the waveforms here are not that much clear here, but the amplitude it has is square root of 2 into 10, while the angle it has is 36.87 as that of the current. The waveforms here are not that much clear, but you have seen all the concept behind the voltages plotting and the phase angles along with them. Okay, so that's it for today, in which we have seen the analysis of a simple series RL circuit, and phasor diagrams, power factors, and many other concepts have been cleared here. So I think it's enough for today, and I will see you with some more questions in our upcoming videos. Thank you so much. Welcome back guys to Engineering Tutor. So again today we are going to discuss the problem number 6 of our book, which is the Introductory Circuit Analysis by Robert L. Boylested. So in this question we are given the voltage and the current which has been flowing through the load here, but what we have to find out, we have to find out the impedance or the total load which has been connected with this voltage source. Similarly, in part B of this question, the same statement of the question has been used, that we have to find the impedance or the internal impedance which is inside this black box. Similarly, here in part C, the black box is again connected, and again we have to find out the impedance. Okay, so let us start doing it from part A, and here we have to find the impedance, and then we have to represent it as a simple series circuit that will satisfy the indicated conditions. Okay, so what are basically the conditions? Conditions are mentioned in the form of the current and voltage. So let me start it with the first question, and in this question we are given the value of current, the value of voltage, and we know that by Ohm's law the value of impedance is Z equal to V by I. Okay, or here V is E, so E divided by I, the value of E is given, that is 120 volts with 0 degree. So 120 volts with 0 degrees, and the current here is also given, and that is 60 amperes with 70 degrees. Okay, with this 70 degrees. So what we have to do here, we can see that both of these quantities are in polar form, and we have seen in our video which was related to the phasors that polar form is one of the most feasible form for the division and the multiplication of two complex quantities. So here it is already in this form. So doing it right away, what I will get, 120 divided by 60, and angles here will be 0 degrees minus 70 here. Okay, sorry. So here I will have 2, because this will cancel out with this one, and here I will get minus 70 degrees. Okay, so here we have this one, and this is in ohms with the minus 70 degrees. But from here we cannot get to know that how much resistive will I have here and how much inductive or capacitive, which is basically the reactive element which we will have. Okay, so in order to do it, here we can see that here we have this voltage, this is E, and the current which is flowing through it is this I, and here the inside of it, this is that black box. Let me represent it with this, okay, and here this one, and inside of it I will have two components. One will be connected here, the second will be in series with it, okay. So it will be like this one. So here this can be the real component, this can be the imaginary component, and from it we can see that which type of component is it. So therefore we have to convert this polar form into the rectangular form, okay. So what we have to do, let me go to the calculator. We can also do it manually, but in order to simplify the procedure here, I am going to use this calculator. So here the amplitude is 2. Similarly, the angle associated with it is basically minus 70 degrees. So minus 70 degrees, okay. So that is basically the quantity, and here we can very easily see that it has already been converted into it. So writing it here, it will be 0.68, okay, and the imaginary quantity is 1.88, okay. With it, I is written here, I am going to write here J. So that is the impedance here, and here we can see that the first element here is the real quantity. So therefore this is the resistance, and as with the reactive element or the imaginary quantity here, negative is written. So therefore this one here is basically the XC, okay. Writing them here, I will get here R and here Jx of C, and the values of these quantities are already available here, and these are these values, okay. Xc is 1.88, which is here, and the value of R is 0.68, okay. So that is the solution of part A. Similarly, in order to proceed here, let me start part B of our question. Again the same scenario, the same formula is applied. Z is equal to V by I. So Z is V is given, that is 80 volts with the angle of 320 degrees, and I is 20 milliamps. So 20 into 10 raised to power minus 3, okay, and the angle associated with it is 40 degrees. So again simplifying them, writing them, what I will get, 80 divided by 20 into 10 raised to power minus 3, here 320 minus 40 degrees, okay. Let me move down again here, calculating it, I will get here this 4 into 10 raised to power 3, and the angle here will be 280 degrees, okay. So this is now an ohm, where this 4 into 10 raised to power 3 is basically the thousands. So again we have to find out the impedance inside of it, okay. So that is basically positive, negative E, while the current is flowing through it, and inside of it we have two blocks. This one is the resistive block, sorry, and also this block, okay. So these two are in series. Here this will be of this will be the real quantity, and this will be of imaginary quantity. So in order to do it, we have to convert this one into the rectangular form. So what we have to do, again let me go here, and here writing 4000, and the angle associated with it is this and 280. Okay, now pressing equal, it will give me 694.6 because rounding it off to the one decimal point, so 694.6, 694.6, and the other quantity with it is, this is again negative, so minus 3939.2 minus J 3939.2. okay, so now this is the impedance of part B, so let me call it Z of P. So here the values, now this one is the value which is for the resistance, and while this one is for the reactance. And which type of reactance is this? This is a capacitive reactance because of the availability of this negative sign with it, so that is X of C. okay, so now writing their values, I will get here this R, and here it will be Jx of C with the negative. So that is for part B, where we again have constructed this circuit where the first element here is the resistor, while the second element is here this circuit. okay, so plus minus V, this is current, and the value of this is 694.6 ohm. okay, and the value of it is minus J 39, sorry, this is 39.2 ohm. okay, so this is the series circuit which we intended to find out. In part 3 of this question, again let me come towards it, and again finding the value of the impedance which is inside of this black box. Okay, what we have to do, again we have to use the same formula, and for that E is 8 kilovolts with the 0 degrees phase, while the current here is of 0.2 amps with the minus 60 degree amps. So here let me start part C. So for part C, Z of C is again V by I. The value of V is how much? The value of V here is 8 kilovolts with 0 degrees. So 8 into 10 to the power 3 with the 0 degrees angle, and divided by the current. The value of current here is how much? 0.2 amps with the minus 60 degrees angle. 0.2 amps with the phase of minus 60 degrees. So now doing it, what I will get again, 8 into 10 to the power 3 divided by 0.2. okay, and the angles here will be 0 plus 60 degrees because now it has moved upward, so the sign with it has been changed. So 8 divided by 2.2 is how much? 8 divided by 0.2 is 40. okay, so now 40 into 10 to the power 3, and the angle with it is 60 degrees, so that is in ohm. Now again the same procedure, the same thing, because what I have to do, I have to find the value of the resistance and also the value of the reactive element which is connected in series with it, while the voltage here is 8 kilovolts with the 0 degree angle, while the current which is flowing through it is I is 0.2 amps with the minus 60 degrees. okay, so here we have to find out the other values which are this resistance and this reactive element. So now in order to do it, what we have to do, we have to convert this one into the rectangular quantity, and from it we will get this Z of C, Okay, so how to do it? I have been doing it by this calculator. So again, writing 40,000 is 41 2 3. Okay, and the angle with it is this, and the angle is 60 degrees. So now writing this equal, and here I will get 20,000 or 20k. Okay, and the other quantity with it is plus j, and with that plus j I have 3 point or 34.641. okay, so that is very huge quantity, 34.6 kilo. Okay, so that is basically the value of the resistor. Okay, while this is the value of the reactance, and here we can see that the sign with this imaginary term is positive, therefore this is basically the inductive reactance. Okay, so writing it x of L, so therefore here this will be x of L, this will be R, and the values these will have will be, this is 20k ohm, while this x of L is how much, this is 34.6k. okay, so that is the solution of our question, in which we have seen that how to find out the value of the unknown impedance if the voltage which has been developed across it and the current flowing through it has been known. Okay, so I hope all these steps, all the things which I have covered in this video are clear now. So that's it for today, and I will see you with some more videos in our upcoming lectures. Thank you so much. Hello all. So again we are going to solve a problem which is related to the analysis of the AC circuit, and the circuit which is given here. In this circuit we have to determine the total impedance which this source can see from these points. Similarly, we have to find the total current, calculate the value of the voltages which are dropped across this resistance and this capacitor as well, and at the end we have to find the power and then power factor. Okay, so let us start it from part A. So in part A of our question here, what we have to do, we have to find the total impedance. Okay, so Z of t, as I have told you earlier that to find the value of Z of t, what we have to do, we have to look for all the real values here, and all the real values are possessed by the resistors here. Okay, so as we have just one resistor, what we have to do, we have to write the value of resistor. After it, what we have to see, we have to look for the reactive elements which are present in our circuit. Okay, so there is only one reactive element, that is the capacitor. Okay, so therefore for the capacitor, what we have to do, for any capacitor I have to write the negative sign with the J, and after it write the capacitive reactance. Okay, so here after putting the values here, we will get the total impedance here, but there is an issue here, and that is we are not given the value of x of c, but we are given the value of capacitance. Okay, so this is, here we have this 0.2 microfarad. Okay, but we don't know the value of x of c. So in order to find the value of x of c, what we have to do, we have to see that this is equal to 1 over omega c. Okay, c is already known here, but what is the value of omega? Omega is again unknown. Okay, so in order to find the omega, what we have to see, we have to look for the frequency which the source has. So we are given here the frequency, and the frequency here is 1 kilohertz. So the frequency here is 1 kilohertz. Okay, so from it I can very easily find the value of the omega. So omega is the radiant frequency, and that is 2 pi f. Okay, now putting their values here, what I will get, omega is 2 pi and 10 raised to power 3. Okay, so that is 2 pi into 10 raised to power 3. Now taking it and putting it into here, okay, what I will get, the value of xc is 1 over 2 pi into 10 raised to the power 3, and the value of capacitance is already known, that is multiplied by 0.2, and micro is 10 raised to the power minus 6. Okay, now simplifying it, what I will get, x of c will be equal to the 1 over 2 pi, this 10 to the power 3 with this 10 to the power minus 6 will be 10 to the power minus 3. So 2 pi into 0.2 into 10 to the power minus 3, and similarly it will be here 2 multiplied by 0.2 is 0.4 pi into 10 to the power minus 3. Okay, or simplifying it again, I will get, moving it to the upper side or to the numerator here, what I will get, 10 to the power 3 divided by 0.4 pi. Okay, now in order to simplify it some more, let me go to the calculator. So in calculator here, let me write the values. So that would be, 1000 divided by 0.4 multiplied by pi. So this is pi. Okay, so what I will get here, this will be 795.77, which is 795.8. okay, so 795.8 ohm. Okay, so that is the value of x of c. Now as we have this equation, and I called it equation A, putting this 795.8 into this one, or let me again use the same convention. Okay, putting it here, what I will get, I will get z of t is equal to, now the value of resistance is 2.2 kilo ohm, writing it here 2.2 kilo, and minus j, x of c is 795.8. okay, so that is basically in ohm, and this is in rectangular form. Okay, let me convert it into the polar form. So that z of t is, so this is 2.2 k, which is 2200. okay, so now let me use it, 2200 minus 795.8 with the iota. Okay, so this one here, or okay, so this one is here. So in order to convert it into the polar form, what we have to do, let me press here 2 and this 3. Now what I will get here, 2339.5, 2339.5 is the amplitude, and what is the value of angle here, angle is minus 19.9. okay, so angle is minus 19.9 degrees, and that is in ohm. Let me write ohm here, and this is the value of the impedance in polar form. So this is the answer of part A of my question. Okay, now similarly, in order to find the value of current here, let me use it here. So now I can see that the value of current is basically E divided by Z of t. Okay, do I know the value of E? Yes, I know the value of E, but that is basically the peak value of the sine omega t. So that's why in order to convert it into the polar form, I should have the RMS value. Okay, so in order to convert the peak value into the RMS value, what I have to do, I have to divide it over the square root of 2, and dividing it over the value which is now Z of t. So as this is the division, so convenient way of using this will be, okay, so the angle with it is basically 0 degree here. So as I have previously stated, the convenient form of the quantities which I have here are the polar forms for the division. Okay, so now I'm using this form of my impedance here, so that would be 2339.5, and that is minus 19.9 degrees. Okay, now what I will get, 20 divided by square root of 2 divided by the square root of 2, I will get here 14.14. So 14.14 divided by this 2339.5. okay, and that is 0 degrees. This will go upward, and here it will get 19.19 degrees. Okay, simplifying it some more, what I will get, this 14.14 divided by 2339.5, 2339.5. okay, so that is almost 6 milliamps. okay, as this is 10 to the power minus 3, so 6 milliamps, and the angle it has is 19.9 degrees. okay, and that is the current, which is part 2 of my question. So 6 amps is the value of the current. Now for part C of this question, I have to find out the voltage drop across the resistor and similarly across the capacitor as well. So now here in part C, I have to find out the value of VR. So as resistor and capacitors are in series, so the same amount of current is flowing through both of them. Therefore, total I multiplied by the value of R. Similarly, the value of C is current multiplied by X of C. okay, but with minus J X of C. So now here the current is already known, and that is 6 milliamps, which is 10 to the power minus 3, and the angle it has is 19.9 degrees. okay, and the value of the impedance was basically 2.2 into 10 to the power 3, which was basically the resistor. So these two will cancel out, and what I will get here, 6 multiplied by 2.2 is how much? 6 multiplied by 2.2 is 13.2. okay, so 13.2 volts, and the angle it has is, phase angle it has is 19.9 degrees. This is V of R. Similarly, in order to find the value of V of C, there I have this 6 into 10 to the power minus 3, and the angle it has is again 19.9 degrees multiplied by Jx of C. What is the value of X of C? That is already known, and that is 795.8. so 795.8, and the availability of this minus J will make it minus 90 degree, which I have previously illustrated in my videos, that why I use this minus 90 degrees or 90 degree whenever I will have plus J or minus J with the imaginary quantities. okay, so it is very easy for you to comprehend here that why I have used this minus 90 degree here. So now multiplying them together, what I will get, so 795, and this is divided by 1000. so let me move here. So here 795.8 multiplied by 6, so this is this one, and divided by 1000 will give me 4.77, which is 4.8 volts. okay, and what is the angle? So 19.9 degrees, and that is minus 90 degrees. So how much would it be? So 4.8, and the angle it will have is 90 minus 19.9, 70.1. So that is, as the larger value here, it has the negative sign, so minus 70.1 degrees. So that is also in volts, and this is what? This is the voltage across the capacitor here. Okay, you can also verify it to see that whether all the voltages available in my circuit obey the KVL or not by using the formula, and that would be E equal to VR plus V of C, and you will see that the phasor sum of VR VC will eventually give you the value of E, and that value will be 20 divided by square root of 2. Okay, so you can very easily find them out by using the procedure which I have previously shown you. Okay, that's it for this part of question. So in part D of in our question, what I have to do, I have to find the value of the power and f of p, which is the power factor. So let me first find the power factor, because that is the important one. So power factor, as I have previously told you, that is r divided by z of t, or is also equal to the cos of theta, where theta is the angle between the total voltage and the current as well. Okay, so let me use this one. Okay, let me use this one here. So in using this one here, so cos of theta is, what is the theta? So the current here we have found out, in the current the angle is 19.9, where the angle with the voltage, phase angle with the voltage is 0 degrees. So it would be cos of 19.9 degrees. So it will be cos of 19.9 degrees, and here I will get 0.94, which is very good angle. 0.94, yes, 0.94. And as the we can see that this is the capacitive circuit where current always leads, therefore I have told you earlier that we have to relate it with the lagging or leading characteristics of the current. So as the current always leads in the RC circuit, therefore this is 0.94 leading. Okay, you can also see it from this formula that it will also give you this value. Okay, so now after it, what I have to do, I have to find the power. So the power here is I multiplied by E, and that would be multiplied with the power factor. So the power factor is cos of theta. So now rearranging it, and I will I multiplied by E multiplied by power factor. Okay, now putting their values, what I will get, so I have is 6 milliamps with the angle 10⁻³ with the angle of 19.9 degrees, and the value of the voltage was how much? That was 14.14. okay, with the angle of 0 degrees, and this was 0.94. okay, so now the power I will have is, multiplying them together, 6 multiplied by 14.14 and multiplied by 0.94, that would be 79.74 into 10⁻³ watts, 79.74 watts. Okay, so that is the power, or we can call it the real power, and from it we have obtained the values which were needed. So that is the end of our question, in which we have found out all the required quantities in our RC circuit, and I hope all the steps which have been covered in this question will be understandable and will be easier for you to grasp the concept. Thank you so much, and I will see you with some more examples in our upcoming videos. Hello again. So, this is another question of the AC circuit analysis, and here again we have to find the similar quantities which we have previously found, but what is the circuit here? That is the circuit which we have to analyze by using the previously established methods. Okay. So, what are basically the tasks here? So, in first part of this question we have to find the total impedance ZT in polar form. Okay. So, again let me start it with this Z of t. Okay, and the similar method here, that we have to write the values of the all the resistors which are available. So, only one resistor is available, and that is this R. So, writing this R. Okay, then after it we have to write the values of all the reactive elements. Okay. So, here in this question we have two reactive elements, and what are those elements? Let me take a look here. This one is the inductor, while this one is the capacitor. So, that is a very conventional RLC circuit. Okay. So, we have to write the values of XL and XC here, and we have previously seen that in order to write the value of X of C we have to put the value of plus J with it, while with X of C I have to write the value of minus J. Okay. So, writing them here as a imaginary components. Okay, and now writing here J X of L. Okay, and similarly X of C. Now, putting their values, what I will get? Z of t is equal to the value of R is 4. Okay, the value of R is 4, the value of X of L is 6. So, this is J 6, while the value of X of C is 10. So, that would be minus 10. Okay. Now, calculating them, what I will get? Z of t is equal to 4 plus J 6 minus 10. Okay. So, ultimately we will get Z of t is equal to the 4 plus J minus 4, or it will be Z of t is equal to 4 minus J of 4. Okay. So, that is basically the Z of t. In order to write them in the polar form, because now this one is the rectangular form. So, writing it in polar form, Z of t will be equal to the magnitude it has. So, again coming over here and writing 4 minus 4, and with this iota here. Okay, it would be this one. Now, converting it into the polar form, this is the third one, and now it will be 4 square root of 2 and minus 45, or it will be 5.65, or it can be 5.7, and the angle is minus 45 degrees. So, 5.7 ohm, and the angle it has is the minus 45 degrees. Okay. So, that is the impedance in polar form for this RLC circuit. What is part B of this question? We have to draw the impedance diagram. In order to draw the impedance diagram here, this is basically the capacitive type circuit here. So, drawing the impedance diagram here, what I will get? This is basically the axis. Okay. This is the axis here, and the total impedance which we have got here. Let me draw each of the impedance here separately. So, using blue color for it. So, for the resistor I have this impedance which is 4 ohm. Okay. For the this is R equal to 4. Okay. Similarly, for the inductor we have this X of L equal to 6 ohm, and for the capacitor which has this resistance is 10 ohm, or I can write it this one. Okay. Because now it has minus J with it, we can write it like this one here. So, this is the real axis, this one is the imaginary axis. Okay. So, taking the cumulative of all these, we have got this one. So, with it the angle is minus 45 degrees. So, from this positive x axis we have to go clockwise direction. Okay. So, in clockwise direction we will have this angle which is now 45 degrees, and the amplitude of this resultant will be 5.7 ohm. Okay, so that is what this is the impedance diagram of this circuit. Now proceeding to the other parts, find the value of C in the microfarads and L in henries. Okay, so we have to find the values of the capacitance and the inductance here as well. Okay, so now to find the values here, this is part C. So first of all, starting from x of L, we know that the value of x of L is omega L. Okay, and ultimately x of L, if we put the value of omega, so x of L is 2 pi f L. Okay, so what is the value of this omega? If we know the value of omega, or if we know the value of 2 pi f, we can very easily find the value of L. So here in coming towards the source here, we can very easily see that this is sine of omega t. Okay, so this is the peak value. So generalized form of this is sine of omega t. Okay, while comparing these two equations, we will get that omega here is 377 radians per second. Okay, so now we know that the value of omega is known, so this one xl is also known, so we can very easily find the value of L from it, which is xl divided by omega. Okay, the value of xl is how much? That is 6, and the value of omega is how much? That is 377. Now calculating it, what we will get? 6 divided by 377, sorry, this one. So now this is 15.9 millihenry, because now this is 0.015. so writing it in the scientific notation, it will be 59.9 millihenry. So this would be 59.9 millihenry. Okay, so that is the value of the inductance here. And we have seen that this is in henries. So if we want to write it in henries, what was that? This was 0.0159. so in henries this was 0.0159 henries. Okay, so that is the value of L. Similarly, in order to find the value of C, we know that x of C is 1 over omega C, or the value of C is 1 over omega x of C. Okay, putting their values here, omega is 377 and the value of x is 10. Okay, so this would be 1 over 3770. So now finding their values, 1 over 3770, so this would be this one. So it is now 2.65 into 10 to the power minus 4, 2.65 into 10 to the power minus 4 farad. Okay, so this is in farad, but here in the question what we are given, that we have to find the values in microfarads. So in order to write the values in microfarads, let me 2.65 into 10 to the power minus 4. So in microfarad we have to make it minus 6, so multiplying it with minus 2 and also with plus 2 as well. Okay, so now this is in farad. Now calculating them, and we will get that C will be equal to 2.65 multiplied by this 10 to the power 2, rearranging it, 2.65 into 10 to the power 2, and here the bases are same, so exponents will be added together. So minus 2 minus 4 and farad, or multiplying 2.65 with this 10 to the power 2, which is 100. So C will be equal to the 265, and here it will be 10 to the power minus 6 farad. Ultimately it will be C is equal to 265, this is 265, and 10 to the power minus 6 is equivalent to the micro, so that would be 265 microfarad. Okay. So, two values are known here, which are the inductance and capacitance values, okay, and we have calculated them very easily from the information which is available in this question. In part D of our question, we have to find the current and the voltages VR, VL and VC in phasor forms. So, again let me start it from here. We have to find the value of VR, we have to find out the value of VL, and we have to find out the value of VC. Okay. So, these three values we have to find out. So, initially in order to find out, we know that this should be IR, this should be I into JXL, or it would be I into minus JXC. Okay. But we do not know the value of I. So, initially first of all we have to find the value of I here. So, I here will be total current will be equal to the voltage divided by the total impedance. Okay. But here we do not know the value of E. We have just the expression of E, but we do not know the values in the phasor form, because now this one is the peak value. We can see that this one is what? This is the peak value, this is omega, and the angle it has is basically 0 degrees. So, this V P should be converted into the VRMS, and we know that VRMS is equal to the VP divided by square root of 2. Okay. So, now let me calculate them here. So, first of all let me calculate the value of in phasor form. So, here it will be Vp divided by square root of 2, and the angle it has is basically 0 degrees. Okay. Vp is how much? 70.7. Let me confirm it here. Yes, that is 70.7 volts. So, here it would be 70.7 divided by square root of 2, and the angle it has is 0 degrees. Now, calculating them again here, 70.7 divided by square root of 2, and it would be 49.99 or almost 50. So, this is now 50 volts and angle it has is 0 degrees. Now, putting these values here, so E is now calculated, and that is 50, and the angle it has is 0 degrees, while the value of Z of t, which is earlier calculated, and that Z of t is 5.7 ohm with the angle of minus 45 degrees, 5.7 and the angle of minus 45 degrees. Now, calculating them, 50 divided by 5.7, and the angles are 0 degrees. It will be here in the denominator, and it will become positive here, and calculating them, 50 divided by 5.7, 50 divided by 5.7, this one is now 8.77 amperes with the angle of 45 degrees. Okay. So, that is now the current which we have. Now, taking this value and putting the value here, the value of current is 8.77 with the angle of 45 degrees, while the value of resistance here is 4 ohm. Okay. So, that is basically the 0 degrees. So, now multiplying it with 4 multiplied by 8.77. So, multiply it with 4, it will be 35 volts, and the angle it has is 45 plus 0 degrees, because both the terms are multiplying together. So, their angles will be added together. This point is cleared in our phasors video. So, if you want to look at that how these two terms are added together, you have to go back to the phasor video, and the link of it I will share over here. Okay, so that would be 35 and the angle of 45 degrees. This is in volts. So this is for V of R. Now in order to calculate the value of V of L, I have to write the value here as well, the current and the angle 45 degrees. Now Jx of L, J is 90 degrees, while the value of X of L is how much? The value of X of L is 6. So this is 6 and the angle is 90 degrees. Okay, so now 8.77 multiplied by 6 is 8.77 multiplied by 6 is 52.62 volts, while the angle it has is 90 plus 45 degrees, so it would be 135 degrees. So this is the V of L, and now the value of V of C is 8.77, angle again 45 degrees multiplied by the value of J minus Jx of C, converting them into the polar form, it would be a magnitude of it will be 10, and the phase angle it has will be minus 90 degrees. Multiplying them together, I will get 10 multiplied by 8.77, so it would be 87.7 degrees, and adding them together I will get minus 90 degrees and plus 45 degrees, I will get here minus 45 degrees. Okay, so that is again in volts. So this is for the V of C. So we have calculated the values of V of R, V of L and V of C, which are mentioned here. Okay, now going forward here, we have to find the and draw the phasor diagram of the voltages E, VR, VL and V of C and current I. So as we have found their values, it is not very difficult for us to draw them here. So this is which part is this? This is the E part. So we have to draw the phasor diagrams. So what we have to draw? We have to draw I, E, V of R, V of L and V of C. Okay, now representing them with different colors. Let me represent I with this red color, this total E with this blue color, while the other voltages, let me this VL and VC with this green color, while again this V of R with let me use this color. Okay, this color. So now let me draw them here. Let me use this one here for the phasor diagram. Okay, so let me first draw the value of E, and that is 50 volts and with the phase angle of 0. Okay, this is E, and E is how much? 50 and 0 degrees. So after plotting the phasor diagram of the total voltage here, let me here plot the value of the current. So the value of the current which we have found here is 8.77 amperes with the phase angle of 45 degrees. So let me calculate it here and see that we have actually calculated it, and let me plot it here. So angle here is plus 45 degrees, so this is 45 degrees. Okay, this is what, this is the current, and the value of current is 8.77 amperes. Okay, so this one is the value of the current. Okay, so after it, let me plot the value of V of R. Let me plot it with this color because I have represented it here. So using this, the value of VR is how much? Let me see here. That is 35 with the angle of 45 degrees. So this is in phase with this current. So here, and the magnitude here is 35. Okay, so 35 is larger than this one, so let me, this one is the V of R. Okay, so and the angle it has is again 45 degrees. Okay, so this is the value of V of R. After it, let me plot, or let me draw the values of V of L and V of C and represent them with this green color. So the value of V of L here is how much? That is 52.62 with the angle of 135 degrees. So this is 90 and 135 almost lie here. Okay, so this is the 135 degrees. Okay, and the magnitude it has is here. This is V of L, and this is 52.62. Okay, so this is the value. Similarly, the value of V of C is, the value of VC is 87.7 and the angle of minus 45 degrees. So again this one, and minus 45 degrees is basically the clockwise angle, and we will start it from here, this positive axis, and clockwise angle will lie here. This will be the angle of 45 degrees. Okay, and this is what? This is V of C. Okay, so that is the phasor diagram which we had to plot in our part E of this question, and we have seen different quantities here which lie here in this diagram, and from this we can very easily see the phase angles associated and magnitudes of different quantities which we have previously calculated. After it, there is part F of this question, and we have to verify Kirchhoff's voltage law around the closed loop. So this is the closed loop, and around it we have to verify the Kirchhoff's voltage law. So in order to verify it, we have to see that this is F. We have to see that whether the total voltage here E is equal to the phasor sum of the this is V of L and V of C. So phasor sum of all the voltages is equal to the total voltages or not. Okay, so in order to do it, let me start it from the left hand side first. So we know that the left hand side we have the voltage here, and that is 50 volts and 0 degrees, and we can also confirm it from here as well, that the total voltage here in the phasor form or in the polar form here we have is this one. Now going toward the right hand side here, we have to see that whether the summation of VR, VL and VC is equal to the total voltage or not. So now writing their values here, the value of V of R is how much? 45 degrees, 45 degrees. Okay, the value of VL is how much? That is 52.62 and 135 degrees, and the angle is 135 degrees, and value of V of C is how much? That is 87.7 and angle is minus 45 degrees, 87.7 with this minus 45 degrees. Now in order to solve it manually, what we can do here, that these are all the quantities which are in the polar form, and we have seen in our phasor videos that in order to add the phasors, it is convenient for us to convert them into the rectangular form first, then we have to add all the real quantities and the imaginary quantities, and after calculating the resultant of all the values in the rectangular form, we have to convert back them into the phasor form. Okay, so that is a feasible method if you are doing it manually. Okay, but we have here is the calculator, and in order to solve them here, let me use the values here. So that is 35, and the angle it is 45 degrees plus 52.62, and the angle is 135 and 87.7 with the angle of minus 45. Okay, so that is the summation. Let me add them and we will get the answer in rectangular form. Okay, so you can see that this is in rectangular form. In order to convert it into the polar form by using calculator, using this one, now 3, and here we will see that this is 49.55, which is almost equal to 50, and the angle it has is almost 0 degrees. This is 0.0 something, which is almost equal to the 0 here. So now writing values here, and we can see that this is almost 50 volt, and the angle it has is 0 degrees, which is almost equal to the value of E. So it says that the right hand side is equal to the left hand side. Okay, so which satisfies the Kirchhoff's voltage law. Okay, so that is a proof of the KVL, that the phasor sum of all the voltages in this loop is equal to the total voltage which we have here. Okay, so that is the solution of part F here. In part G, we have to find the average power delivered to the circuit. The same method which we have previously seen, that by using it we can write here IE and the angle between them, which is cos of theta. This cos of theta is the power factor, which is cos of theta, or we can also do it by using R by Z of t. We have done it previously. Similarly, in part D, find the power factor of the circuit, which is this one. By finding the average power, we have also have to calculate the value of the average power and indicate whether it is leading or lagging. Okay, so that is a very important thing here which we have to see here. So here in the diagram or in the impedance here, we can very easily see here and here and here, see that this is now the circuit of the capacitive nature, because the capacitive reactance is dominant here due to the availability of this negative sign with the imaginary term here, and also this negative angle. So that is the capacitive nature, in which current leads and voltage lags. So when current leads, so therefore power factor is also leading here. Okay, so for this part we have to find the power factor, which is from the cos of theta, where theta is the angle between E and I, or we have to find the ratio between the resistor and the total impedance here, and we have to use their magnitudes here, and we will see that power factor is known, and after it, to see whether it is leading or lagging, we have to see that whether the circuit is capacitive or reactive or inductive. So as the circuit here is of capacitive nature, so the power factor will be leading here. Okay, after it, we have to find the sinusoidal expression for the voltages and currents. We know all the voltages here, which are now in these forms. Okay, these are basically the average voltages or the RMS voltages. So in order to find the, let me use the VR, and in order to find it in the sinusoidal form, what we have to do, we have to write Vp sine of omega t plus theta. Okay, do we know the value of theta in voltage here, yes, we know the value of the voltage here, and that is the total voltage or the RMS value here is 3545 degrees. So let me see that. So V of R with us is 35 volts and 45 degrees. From it we can see that the peak value here is the 35 multiplied by the square root of 2. Why? Because the RMS value is always equal to the VP divided by square root of 2. So now in order to find the value of V of P, we have to multiply this square root of 2 with the RMS value. Okay, so this RMS value is given here, which is this 45 degrees, which is also mentioned here. Okay, so we have to find this value and then put it here. Also the value of theta is also given, and this is here. Okay, so now let me use this red color. So this is now the value. Okay, and we have to put it here. Okay, similarly the value of theta is 45, we have to put it here, and ultimately what we will get, the value of VR will be equal to the 35 multiplied by square root of 2 . This is 49.5, so it will be 49.5 into sine of omega t. Do we know the value of omega? Yes, we also know the value of omega, and that is 377. Okay, so writing the value of omega here as well. So 377 t, and the angle it has is 45 degrees. So this is the expression for V of R. Similar method we can use for other quantities, just like V of L, just like V of C, where the angles and the RMS values and angles are also given. In order to find the value of the peak value from this RMS value, what we have to do, we can use this formula. Okay, and from it we can also use this formula as well, while theta would also be here, and theta will be given similarly for this one as well. So that is the solution of our I, and from it we can also plot the values of all the waveforms in the time domain. Okay, which we have covered in our previous videos as well. So that's it for today, in which we have discussed this RLC circuit, and we have calculated all the required values by using the methods which are mentioned in our book. So thank you so much. Take a look over all the steps here and grasp the conceptual overview of these type of circuits. Thank you so much, and I will see you with some more examples, more questions in our upcoming video. Hello again, welcome back guys. So this is question number 12 of our book, and in this circuit we are given a very simple series configuration of the two resistors, in which the source voltage is known, which is the RMS value, and similarly the scope or the oscilloscope is also connected here across this 80 ohm resistor, and from it we have seen that the calculated peak to peak voltage it has is 45.27 volts. So what is the peak to peak voltage? So let us have the voltage waveform across this resistor is basically this one. Okay, so this is the VP, while this is the minus VP. Okay, so this VPP is basically this peak to peak voltage, which is this V peak to peak, and we have known it, and this is given here. Okay, as this is a symmetrical waveform, so in order to find the value of VP from these type of waveforms, what we have to do, we have to divide our peak to peak voltage over 2. Okay, so in the symmetrical waveforms we will get the peak values from this expression, and it will be writing 45.27 divided by 2. We will get how much? 45.27 divided by 2, this will be 22.6 volts. So that is the peak waveform. Just you have to remember that this formula is valid for all the symmetrical waveforms. And what are the symmetrical waveforms? The waveforms where the DC term is the 0 volts, okay, or which originates from the origin and get back to origin, okay. So this is the symmetrical waveform where the values at the positive cycle are equal to the values in the negative cycle, okay. So in that case we have this peak waveform. So in that case our peak voltage value is the half of the peak to peak value, okay. So we have calculated it. After it, you know that this is the peak value here, so we have to find the RMS value from it, because all the calculation here will be done in the form of the RMS or the effective value. So RMS of this value, or let me call it V80. So 80 here is 22.6 divided by square root of 2, okay. So now calculating it here, what we will have, let me use it, 22.6 divided by the square root of 2, so it will be 15.9, and that is almost equal to the 16 volts, okay. So here we have this value. Now as we know the value across this resistor as well, and in order to find the value of this resistor, what we can do, we actually have the voltage across this one, and I have earlier told you with every element we have three quantities associated with them, what are basically the current, voltage and impedance, okay. So if any two of those are known, we can easily find out the third one, okay. So here we don't have the current, we don't have the voltage, and we don't have the impedance or the resistance here as well. So what we have to do, first of all we have to find out the voltage, and from the voltage we have to find out the current, and after the current we can find out the value of impedance, okay. So that would be a very lengthy process. As we know the voltage across this 80 ohm resistor, in order to find the value of this resistance here, we can here use a trick in which the value of R will be included and all the other quantities will also be included. So we can use here the voltage divider law at this resistor, okay. So in order to find the value of V80, we have the voltage divider law, in which the value of the resistor across we want to find out the voltage is known, and also the summation of all the resistors which are connected in series multiplied by the total voltage, okay. So that is known here. Do we know the value of V80? Yes, we also have the value of V80, and that is 16. So 16 is equal to the 80 multiplied by 20 divided by R plus 80, or that is 16 R plus 80 is equal to the 1600, okay. Now in order to find the value of R, let me simplify it, and it will be R equal to the 1600 divided by 16 and here minus 80. So this will be cancelled out, and here 100 will be left out, and here R will be equal to the 100 minus 80. So the value of R will be equal to the 20 ohm, okay. So that is the value of the resistance which we had to find here, okay. And this is the method which we have used, and a very convenient and a very shrewd trick which we have used here in order to find out this value. So this is basically the concept that how you can use other methods in order to find the quantities by using the concept of the other techniques which we have so far seen, okay. So thank you so much, and I will see you with some more tips, more tricks and more solutions of the circuits like this one in our upcoming video. Thank you so much. Welcome back, guys. So this is question number 13 of our book Introductory Circuit Analysis by Robert Boylested, and here we are given this circuit in which we have this digital multimeter readings for the current and for the peak to peak voltage as well. With this peak to peak voltage is basically calculated from the oscilloscope, okay, while this one is calculated via digital multimeter. Okay, so from it what we have to calculate, we have to determine the value of L, which is this one, and also the value of this resistance as well. Okay, so let us proceed here. So part A of our question, we have to find out the value of L, and we know very well that to find L, let me have the expression for V of L, and for V of L I know that V of L is I x of L. Okay, this is equation A, and also from x of L we know that x of L is omega L. Okay, this is equation B, and here omega is equal to the 2 pi f. This is equation C. Okay, so now in order to proceed here, let me first find my quantities here. So this one, the total voltage here or the source voltage here is basically in RMS, the current is in RMS, while the value of the voltage here is basically the peak to peak voltage. Okay, so I have recently covered that how this peak to peak voltage seems like. So let me have it, this V peak to peak, and that is 21.28 volts. So now in order to find the Vp in the symmetrical waveform, what we have to do, we have to 21.28 divide it over this two. So what I will get here, let me use the calculator here. So here 21.28 divided by 2, so it will be 10.64. so this is 10.64 volts, while this one is the peak voltage. I know previously that Vrms is equal to the Vp divided by square root of 2. So let me use the same procedure here. So 10.64 divided by square root of 2, how much would it be? So dividing it over square root of 2, I will get 7.5 volts. Okay, so writing it here, 7.5 volts. This is the RMS value of V of L. So this is V of L. Okay, so I know the value of V of L. I have the value of current here, which is same here, because this is a series circuit which is consist of these two elements. So this equation satisfies, but how to find the value of omega? So let me start it from C here. So let me write values here. So 2 pi, and the value of f is also given here, that is the source frequency, and that is 1000 hertz. Okay, so writing it, 1000 multiplied by 2 is 2000, 2000 multiplied by pi is how much? 2000 multiplied by 3.14, and that would be 6280. So that is 6280 radians per second. Okay, now taking it from here, okay, and putting it here. Okay, when I will put it here, what I will get here, I will get here the value of x of L will be 6280 multiplied by L. Okay, so this is the expression for x of L. Now taking this one, okay, and putting it over here. Okay, so now let me use it. Okay, so V of L is I x of L. Putting the value of x of L, what I will get, VL is equal to the I multiplied by 6280 6.80 multiplied by L, okay, or the value of L here is how much? L is VL divided by I into 6280. Do I know the value of V of L? Yes, it is known, and that is 7.5. Do I know the value of I? Yes, this is also known, and this is the 29.94 milliamperes. So 29.94 milliamps, which is 10 to the power minus 3, and that is here 6280. Okay, so now let me simplify it. So 7.5 divided by how much? So let me use this expression as a denominator of this equation. So 6280 multiplied by 29.94. okay, so this would be this one, and dividing it over 1000, because this is 10 to the power minus 3. So how much it would be? It would be 188. Okay, this is almost 188. Okay, so now simplifying this one again. So 7.5 divided by 188, this is 0.0398, 0.0399. okay, so this is the value of the inductor, or if you want to find it in the millihenry, so in millihenry it would be 39.9 millihenry. So that is the value of the inductance which we had to find out. Okay, so through this procedure we have found out all these values. Okay, so that is the part A of our question. So in order to proceed, what we have to find out, we also have to find out the value of resistance here as well. So now to find out the value of this resistance here, what we have to do, we know that with every element we have three quantities associated. What are those quantities? The current, the resistance or impedance, or the voltage. Okay, so these are the three quantities. I have previously stated that if any of the two quantities are known, we can very easily find out the third quantity as well. Okay, so we know the current here, but we don't know the voltage here. Okay, so let me first find the voltage here in part B. So in our question here, we can very easily see that here the phasor sum of total voltages across elements is equal to the source voltage. Okay, here we have these two elements, inductor, resistor, and then this source voltage here. So the phasor sum of the voltage which is consumed across this resistor and the inductor here is equal to the source voltage. Okay, so how to use this equation here? So now here we can see that E is equal to the phasor sum of VR and VL. Okay, so this is basically the phasor sum. Why am I using the phasor terminology or phasor summation over and over again? Because here we can see that resistor is basically the real quantity, and in resistor we have, this will be the voltage. Okay, because no phase shift can occur. But when we consider this V of L, we will see that V of L is equal to the I j x of L, which is I multiplied by x of L with an angle of 90 degrees. Okay, so this j is basically corresponds to this 90 degrees, therefore it will lie here, at positive axis, so it will be x of L, and it will make this angle here. So these are basically the quantities, and to find the value of E, what would we found out here, we will see that it will be somehow like this is V of L. So now in order to find it out, let me plot their values. So here this will be VR, okay, this will be VL, and the source voltage will be here. So this is here, okay. So here what we have to find out, we have to find out the value of V of R. So therefore in this, let me use the Pythagorean theorem. So according to that, E is equal to the VR square plus VL square, so that is equal to E square. So now in order to find the value of VR will be equal to the E square minus VL square whole square root. So let me use these values here. Do I know the value of E? Yes, it is also known, and it is 10 volts. So 10 square minus what is the value of V of L. So the value of VL is also known, and that is 7.5. 7.5 whole square root. Okay, so let me use calculator here. So 10 square minus 7.5 square, it will be 43.75, and square root of 43.75. so let me 43.75, this is V of R, or the value of V of R will be equal to how much? Square root of 43.75, it will be 6.61. So this is 6.6 volts. So the value of VR is 6.6. Okay. Now to find the value of resistor, here let me use the Ohm's law. So V of R is equal to the I multiplied by R, or the value of resistance is VR divided by I. I know the value of V of R, that is 6.6, and the value of current is how much? It is already mentioned here, and that is 29.94 milliamps. 29.94 into 10 to the power minus 3. So it will be 6.6 divided by 29.94 into 10 to the power 3. Okay, so let me calculate it. 6.6 divided by 29.94, so it would be 0.220. So 0.220 to 10 to the power 3, or ultimately I will get here 220 ohm, because this is 1000 multiplied by 0.220 is 220 ohm. Okay, so that is the value of resistance. So in this question we have found out how to use the values calculated from the oscilloscope and digital multimeter to find the values of the unknown quantities which are available in our circuit. Okay, this is somehow like a practical example in which in many scenarios, in many circuits, we don't know the internal configuration of any circuit, or inside the black box we don't know the quantities available. So at the output of our system we can connect the oscilloscope, digital multimeters, and can very easily find out the internal configuration of our circuit. Okay, so that's it for today, and with some more interesting questions I will see you in our upcoming video. Thank you so much. See you soon. Hello again, guys. So another very interesting question, in which we are given the reading of the oscilloscope to find the unknown quantity here, and that is the value of the capacitance which is inside the black box, and we just have the value of the peak to peak voltage across this resistor. Okay, so how to use these values here? So let me first convert this peak to peak voltage into the RMS value. So in order to do it, let me use this V of R is equal to the 8.27 divided by 2. Okay, so it would be the peak value, because this is a peak to peak value, and at the end I have to divide it over this square root of 2. So I will get here 827, okay, 8.27 divided by 2 into square root of 2. Okay, so why to use this square root of 2? Because I have previously mentioned that Vrms is equal to the V peak divided by square root of 2, and using this similar concepts here, and similarly Vp is equal to the V peak to peak divided by 2. Okay, putting it here, and then using this mechanism to find the values, the ultimate numerical values will be here. Okay, so I have also mentioned all these concepts in our previous videos. So now simplifying it, I will get, so 8.27 divided by 2, so it is 4.135 divided by square root of 2, 2.92. okay, so that is basically 2.92 volts, and that is V of R. Okay, as I already know the value of VR now, so by using the voltage divider law in this circuit, I can see that V of R is equal to R divided by R plus X of L multiplied by what? Multiplied by the source voltage, and that is E. Okay, now putting their values here, what I will get, this will now, or rearranging it to find the value of X of L, what I will get, V of R, R plus X of L equal to R multiplied by E, or VR multiplied by R plus VR multiplied by X of L is equal to R multiplied by E, or to find the value of X of L, subtracting VR multiplied by R in both sides, what I will get, VR into X of L is equal to R multiplied by E minus VR multiplied by R, or from here I can also see that it will be R E minus V of R whole divided by V of R, and that is equal to the X of L. Now putting values here in this equation, so let me call it equation A. Putting values here, what I will get, the value of R is given, and that is 10 kilo ohm, that is 10 into 10 to the power 3 for the simplicity. What is the value of E? E is also known, and that is 12 volts. 12 minus what is the value of V of R, the voltage which has been detected across this resistor. So that is already known, that is 2.92. okay, whole divided by V of R. So whole divided by V of R is 2.92. okay, so now let me simplify it. So for simplifying it, let me first 12 minus 2.92. okay, so it will be this one, 9.08 and 9.10 to the power 4 into 9.08 divided by 2.92, or divided by 2.92 92, this is 3.10, and times power 3 multiplied by 10 into 3.10, or it will be 31 into 10 to the power 3, or ultimately it will be 31 kilo ohm. Okay, so that is the value of X of L which I had to find out here. Okay, so from our previous expressions I know that the value of, that is X of C. Let me now use X of C here instead of this X of L, because this is the capacitor. So X of C is 31 kilo ohm. As I know that X of C is 1 over omega C, or the value of C is 1 over X of C multiplied by omega. Now let me put their values. So X of C is how much? That is 31 into 10 to the power 3. Okay, what is the value of omega? That is 2 pi into f. Okay, so it will be 31 into 10 to the power 3 into 2 pi into what is f here. So f is 40 kilohertz. 40 into 10 to the power 3. So here it will be, capacitance will be here, and that would be, let me move this 10 to the power 3, 10 to the power 3 is 10 to the power 6. So 10 to the power minus 6 in the numerator, and here 31 into 2 pi into 40 is how much? 80 pi. Okay, so now let me calculate it. 31 into 80 into 3.14, it will be like here, and taking reciprocal of it, what I will get? So reciprocal of it will be this one. So this is 1.28 into 10 to the power minus 4. So 1.28 into 10 to the power minus 4 into 10 to the power minus 6. So it will be how much? 1.28 into 10 to the power minus 10 farad. Okay, so that is the value here, and in order to convert it into the nanofarad, what I can do here, now let me use here 0.128 into 10 to the power minus 9 farad. Okay, so ultimately I will get here 0.128 nanofarad. So that is the value of the capacitance or the capacitor which I had to find out. So that's it for today, in which we have found out the value of the capacitor in this question. So I will see you with some more question in our upcoming videos. Thank you so much. Hello guys. So today we are going to discuss the voltage divider law in our AC circuits. So if you recall, we have discussed the same rule or law in our DC circuits. So what was basically the voltage divider law? So suppose we have a voltage source here, and with this we have different impedances connected in series. Okay, just like this one and this one here as well. Okay, so if we have these impedances connected, so let me call it Z1 and this is Z2, and this is, let me call it E, or the source voltage. Okay, so let me have the voltage drop across Z1 is V1, and similarly let me represent it with the red color. This is V1. Okay, and across Z2 I have V2. Okay, so now in order to find the value of V1, V2, what we have to do, first of all we have to calculate the current, and after calculating the current we have to find the V1 and V2 by using Ohm's law. Okay, so we are again at the mercy of the current. So in order to remove the dependency upon the current. What is here? We have the voltage divider law, and in order to find the voltage divider law, what we have to do here, in order to find the value of V1, what we have to do, we have to write the impedance across which we have to find the voltage and divide it over the equivalent resistance, which is in this case, basically in this series case, is the summation of all the resistances which are connected in series. Okay, and at the end we have to multiply it with the source voltage. So that is the voltage divider law, and through which we can calculate V1, V2, V3, whatever we want to calculate. So if this is V1, so V2 can be calculated by V2 is, so now V2 is across Z2. So in numerator we will have Z2, and as the equivalent resistance will remain same here, so therefore it will be Z1 plus Z2 here, which will be multiplied with this total voltage. Okay, so now here we can see that in our part A of question 15, we have to calculate the values of V1 and V2 with the given source voltage and the given resistance is here, or the given impedance is here. Okay, so what we have to do, so here this is the same circuit here, while the value of Z1 here is 2 kilo ohm, while the value of the Z2 is 8 kilo ohm. Okay, while this is R, while this is X of L. Okay, because this is the inductor, so that is the inductive reactance, while the value of the source voltage is 120 volts and the angle it has is 60 degrees. So now let me put values here in order to find the value of V1. So what will be the value of Z1? So Z1 is 2 kilo ohm, which is already known. Okay, that is 2 kilo ohm divided by Z1 is again 2 kilo or 2000, and plus I have to write the value of X of L. But wait a minute, this is the inductive reactance, and inductive reactance cannot be directly added with the linear resistance. So what we have to do, I have to use this J here, and this is now 8 kilo ohm, which is 8000 multiplied by the value of the source voltage, that is 120 with an angle of 60 degrees. Okay, so now here we can see that all the operations here are either multiplication or division. So the feasible form here will be the polar form. Okay, so now I have to convert them into the polar form, and in order to convert them into polar form, let me convert first this one into polar form. So as this is a linear element or the resistance, so this is 2000 and the angle it has is 0 degrees multiplied by 120 this one, and the angle it has, this is already in the polar form, it is 60 degrees divided by the 2000 plus J 8000. Okay, so that is the rectangular form. Let me convert it into the polar form. So 2000 plus 8000, okay, with the iota here. Okay, so now I have this number, and in order to convert it into the polar form, let me use this one. So it will be 8246 point how much, 21 or 2. Okay, and the angle it has is how much? Angle is 75.96 degrees. Okay, so now I have this term here. So the value of V1 will be how much? So V1 will be 2000 multiplied by 120 whole divided by 8246.2. Okay, and the angles, these two are multiplying together, so therefore 0 degrees plus 60 degrees, while this is in the denominator, so therefore it will be subtracted from it. So I will have 75.96 degrees. Okay, so now let me find it. So V1 will be equal to how much? 2000 multiplied by 120, so that is 2,40,000 divided by 8246.2. 0.2. Okay, so that is now 29.10 volts with an angle of, this is 60 minus 75 is minus 15.96 degrees. So this is the value of V1, or the voltage which is dropped here, or the voltage here which is now across 2 kilo ohm resistor. Okay. Similarly, in order to find the value of V2 here, I have to use Z2 divided by Z1 plus Z2 multiplied by E. Okay. Now putting their values, the value of Z2 is how much? This is now the Z2, which is X of L. So as this is the inductive reactance, so therefore it will be J 8000 divided by Z1 is again the same value it has, and that is 2000 plus J 8000 and multiplied by the 120 with the 60 degrees here. Okay, so now let me simplify it some more. Okay, so this J 8000 again in the polar form will be 8000 with an angle of 90 degrees multiplied by 120 with an angle of 60 degrees. Okay, so while this one is here same as that of the previous one, and previously we have calculated the polar form of it, and that was 8246.2 with an angle of 75.96 degrees. Okay, so now let me simplify it. So 8000 multiplied by 120 whole divided by 8246.2, while the angle it has will be 90 degrees plus 60 degrees, while this one, the denominator term, will be minus 75.96 degrees. Okay, so now let me calculate it, and calculating it I will get it here. So 8000 multiplied by 120, this is this one divided by 8246.2. okay, so how much it would be? It is 116.4. so 106, and the angle it will have will be 90 plus 60 minus 75.96. so it will be how much? This is now 74.04. okay, so the angle I have is basically the 74 point how much? 04. So that is the voltage which is basically the V2. So in this question we have found out the voltages which are here. So by using the voltage divider law, we have developed a mathematical formulation here, and after that mathematical formulation we have found our values. Okay, so this is part B, and we will solve it in our next video. So you are supposed to try these things by yourself and see whether the results are correct or not. Okay, so thank you so much, and I will see you with some more question in our upcoming video. Welcome back, guys. So today we are going to start part B of our question 15. So what is in part B? So here again we are going to find the value of V1 and V2 by using the voltage divider rule. Okay, so again following the same procedure here, but first of all let me calculate the total impedance. Okay, so the only difference between the previous circuit and this circuit is that previously we had two impedances. The first one was the resistor, while the second one was the inductor, while here we have three impedances, and from these three we have to find the voltages across two of them. Okay, so what do we have to do? Many students find it difficult to calculate the voltages across the subset of the elements if more than the desired number of voltages impedances are available. Okay. So, here we want to find out Z of t. So, Z of t is what? So, here we have this resistance, this impedance and this impedance as well. So, let me calculate them. So, 6.8 okay, plus J40 which is for this inductive reactance, okay, and similarly this 22. Now, calculating it, what I will get, Z of t will be equal to 6.8 plus 22 real was with real and plus J40. Okay. What will we get here? So, ultimately total impedance will be 6.8 plus 22 is 28.8 and this is plus J40. So, this is the impedance in rectangular form. What we have to do, let me change it to the polar form as well because we may need it. So, that Z of t is 28.8 plus 40 with the iota here. So, where this one, okay, or this one here. Okay. Now, converting it into the polar form, let me press shift and then this and now 3. So, it will be what? 49.28, 49.3, okay, and that is the ohm, while the phase angle associated with it is 54.25, 54.25 degrees. Okay. So, that is the total impedance. Now, what we have to do, let me represent this one with V1. We want to calculate this V1 and also this V2. Okay. So, now let me calculate them here. So, we know that according to the law, V1 is equal to, that is V1 and that is equal to this 40 ohm inductive reactance. So, here it would be JXL or J40 divided by the total impedance which is already calculated here. So, that would be 49.3 with an angle of 54.25 degrees, okay, and multiplied with the total voltage which is which is this one here, that is E equal to 60 volt with the 5 degree here. So, 60 with the 5 degree. Okay. So, now all the terms here I can see that the operations involved here are basically the division and multiplication. So, all the terms should be in polar form in order to calculate all the required quantities in a very simplified or easy manner. Okay. So, therefore, this one is basically in the rectangular form. So, let me convert it into the polar form. When it will be converted into polar forms, J will be removed here and it would be here 90 degrees, okay, because I have previously explained in the video which I will again put link over here. So, it will show you that when you will remove J from here, you will have to use the angle of 90 degree. Okay. So, now let me calculate the value of V1. So, value of V1 will be 40 multiplied by 60 divided by 49.3. These are all the magnitudes of all the phasors. Similarly, the angles here are 90 degree, which are all the numerators. So, plus 5 degree, these are the numerators here, while the denominator term will be subtracted from here. Okay. So, now let me calculate them. So, 40 multiplied by 60. So, that is 2400 divided by 49.3. So, it would be how much? That is 48.68. Okay. And as this is in volts, so let me write volt here. And now, in order to calculate the angles, so what I have to do, let me write here 90 plus 5 minus 54.25. Okay. So, that would be how much? It would be 40.75. 40.75 degrees. So, that is the value of V1. Okay. Similarly, now in order to find the value of V2, let me use the green color here, and that is V2, and the concerned value of the resistor across which I want to find out the voltage. So, that is 22 divided by the total impedance. Okay. So, 22 ohm divided by the total impedance, which is 49.3 with the angle of 54.25 degrees, and multiplied by the total voltage, and the total voltage applied across it is 60 with an angle of 5 degrees. Okay. So, here V2 will be equal to, as this is a resistor, so resistor is basically the linear term. So, the angle associated with it will be 0 degrees. Okay. So, here it would be 22 multiplied by 60 divided by 49.3, it would be, and here the angles will be 0 plus 5 degree, because both are here in the numerator and the denominator term will be subtracted here. So, 54.25 degrees. Okay. So, now let me calculate it. Okay. So, 22 multiplied by 60, that is 1320 divided by 49.3, and it would be 26.77 volts with an angle of, here let me use it. So, 0 plus 5 is 5, 5 minus 54.25 is minus 49.25 degrees. Okay. So, that is the value of what? That is the value of V2. Okay. So, that is it for today, in which we have calculated the values of V1 and V2 in part B of our question. Here the sole difference between the circuits is that here we are having these three resistors, but what I want to find out? I want to find out the voltages across the other two resistors. So, students usually make it very difficult to find the values here, because they see that these are the two resistors. Okay. So, they usually find the impedance or the total impedance, which is the combination of J40 plus 22. Okay. But that basically is not the total impedance. Total impedance also consists of this one. Okay. So, that is why I first of all calculated the value of Z of t, which is basically composed of 6.8, J40 and then 22. Okay. So, that is the essence of this question, in which I have solved the mystery of these type of circuits. Okay. So, that is it for today, and I will see you with some more interesting questions in our upcoming video. Thank you so much and see you soon. Welcome back, guys. So, here question number 16, and again the same scenario, in which we have three resistors and we have to find out the voltages across two of them. Okay. So, now what is the first step here? So, this is the same circuit like we had previously. So, this is the voltage source. Okay. We have basically three impedances here. Okay. And we have to find out the value across Z2 and Z3. Okay. So, for it, what we should have? We should have the total impedance here as well. So, let me represent this one with the red color, while this one with the green color. Okay. So, for it, let me first calculate the total impedance. Okay. So, the total impedance here is Z of t, and as this is the series circuit, so the total impedance will be consist of a series combination of this resistor, this inductive reactance and this capacitive reactance. Okay. So, let me write the values here. So, this is the real value, which is the resistance here. So, 20 plus, as this is the inductive reactance, so J20, okay, while this is a capacitive reactance. So, I have to put minus J with it. So, minus J40. Okay. So, here what I will get, it will be Z of t, and Z of t is real term, while this one will be plus j 20 minus 40, and ultimately I will get here z of t is equal to the 20 minus j 20. Okay, so that is the impedance in which form? This is the rectangular form. So let me calculate it in the polar form as well. So for polar form I can use this one here. So 20 minus 20 with the iota here, so it will be here. Now similarly this complex, this 3. Okay, so here I will get this one, or 28.28 ohm with an angle of what? Minus 45 degrees. So that is the total impedance. Okay, so now let me calculate the value of V1 here. So the V1 is across this inductive reactance. So V1 is J20 divided by the total impedance, and that is Z of t, that is 28.28 with an angle of minus 45 degrees multiplied by the total voltage, and the total voltage which is given here is 20 with an angle of 70 degrees. Okay, so you can very easily see that the operations which I have to perform here are basically the multiplication and division, and the feasible form for these operations is basically the polar form. Okay, so all the quantities if will be in the polar form, so the calculation or the steps I have to perform will be very feasible for me. So here let me see that this is basically in polar form, this is in polar form, while this is not in polar form, this is in rectangular form. So let me change it into the polar form. So removing j, I have to put 90 degree here. Okay, so it is now in polar form. So now calculating V1, this would be 20 multiplied by 20 divided by what? 28.28, and the angles here are 90 degrees plus 70 degree. These are the numerators, and here this is minus 45, so it would be plus 45 degrees. Okay, so now let me calculate them. It will be what? 20 multiplied by 20, so it is 400 divided by 28.28, and it would be 14.14 volts, while the angle with it is how much? Let me add them. 90 plus 70 plus 45. So here I will have 205 degrees. Okay, so that is the value of V1 which I had to find out here. Okay, similarly now finding the value of V2, what it would be. So the impedance across which I have to find out it is basically the capacitor here. So I have to find out the voltage drop across this capacitive reactance. So it would be minus J40, okay, divided by the total impedance, and that is already calculated, and that is basically 28.28 with an angle of minus 45 degrees. Okay, and multiplied with total voltage. So the total voltage is again already found out here, and that is 2070 degrees. Okay, now let me calculate the value of V2 again following the same steps. Okay, so first of all let me convert this minus J40 into the polar form. So it would be in polar form here, which will be minus 90 degrees. You know why? Because when plus j is equal to the 90 degrees on the Cartesian or the complex plane, so minus j will be equal to the minus 90 degrees. Okay, so now similarly using 40 multiplied by 20 divided by 28.28 with an angle here of minus 90 degrees plus 70 degrees, and here this would again be plus 45 degrees. Okay. So now let me calculate it. It would be 40 multiplied by 20, 800 divided by 28.28. So that is how much? That is 28.28. 28.28, and the angle here will be how much? That would be minus 90 plus 70 plus 45. So it is 25 degrees here, 25 degrees, and as this is involved, so it is here. So that is the value of V2, which is across this capacitive reactance. Okay. So these are the values which I had to find out, and this is the solution of question number 16 of our book. So that's it for today, in which we have seen that how to calculate the values of voltages across different elements in a simplified RLC circuit. Thank you so much, and I will see you soon. Welcome back, guys. So this is question 16 part B of our book Introductory Circuit Analysis by Robert L. Boylested. So what we have to find here, so previously we have seen that we had to find out the voltages across the elements of our circuit, but here we are given to find out the values of V1 and V2, while these V1 V2 are not the potential differences but are the point voltages. Okay, so we can see here that these are the voltages which we can find out. Okay, so similar concept has also been explained in one of my video, and I will put the link of that video in our description here. So you may see here that what would be the value of voltage here. So there are basically 2 or 3 methods to calculate the voltages at these points here. So what are basically those methods? So let me first describe them here. So if we have the impedances like this one, okay, and this is basically the source. This is, let me call it Z1, and this is Z2, and the source voltage here is, let me call it V of S. So the voltages across different points here are known. So let me call this voltage as V1 and this V2. Okay, so this is plus minus V1, this is plus minus V2, and let us have this point which is, let me call X, and if I want to find out the voltage at V of X, how can I find it out? I should have to use this Vs, and I have to subtract this V1 from this Vs, and then I will get this V of X, which is basically the voltage with respect to this ground, okay, or this reference point. Similar approach can also be used here, but in order to tackle the issues here or simplify my calculations, I am going to use another method here, and in that method what I have to do, let me again draw a simplified version. Okay, so this one and this one here. Okay, so let me divide my impedances into 2 voltages, which are this Z1 and this Z2. Okay, so let us have this Z1 equal to 4.7 kilo ohm. Okay, and all the remaining resistors are basically here. So what we have to do, if I want to find out the value of V1 here, okay, so that V1 is basically which a circuit or the source has to consume overall across this one, and here I will get this voltage equal to 0, because according to the KVL all the voltage will be consumed across all the elements or impedances connected in a circuit. Okay, so that's why the voltage which is here will be consumed across this one. So actually to find out this V1 I have to find out the voltage across this Z2. Okay, so the question is what will be the value of Z2. So Z2 is basically the series combination of this 30 kilo ohm, 3.3 kilo ohm and 10 kilo ohm. Okay, so now let me calculate the value of Z2. So Z2 is how much? This is the inductive reactance. So let me represent it with this J30K. Okay, similarly this is a resistor here, so 3.3K. Okay, and this is a capacitor, so let me represent it with minus J 10K. Okay, so let me simplify it. So Z2 is equal to, using this one here, 3.3K and similarly plus J 30K minus 10K, because it is these two are added together and I have got this one. Now here Z2 is 3.3K plus J, this one is this is 30K here, so let me, this is 30K here, so I will get here 20K. Okay, so this is my Z2, or in polar form what I will get here, in polar form I will get it, this 3.3 is 3300 and plus this is 20,000, 1 2 3, so that is 20,000, and with this I will have this iota, so this one here, and let me convert it into the polar form. Okay, so it would be 20 to 70 point how much, 0.42 with an angle of how much, 80.63. So 80.63 degrees, and that is basically in ohm. So that is the value of Z2, which is the resistance across which I have to find out the voltage. Okay, so after it, what I have to do in order to find the voltages across all of these elements, I should also have the total impedance here as well. So the total impedance here will be Z of t is equal to Z1 plus Z2. Okay, so that is basically the total impedance. So I just have the value, that is 4.7K, and the value of Z2 is already known. So let me use the value here which is mentioned. So 3.3K plus J 20K. So when these two will be added together, what I will get? I will get 8K plus J 20K. So that is the total impedance. Okay, in order to calculate it in polar form, what I have to do? So let me calculate it in polar form. So 8K is 8000 plus 20, 1 2 3, this one. Okay, so that is Z of t, and now converting it into the polar form, this one, so that is 21,540.66. Okay, and the angle it has is how much? That is in ohm. So let me use this omega here, and the angle it has is 68.19 degrees. So that is the total impedance. Okay, now I have to find out the voltage across this Z2. So let me move it down. I want to find out the voltage across this Z2. So in order to do it, let me use the voltage divider law. So according to the voltage divider law or voltage divider rule, this is basically V1 in our circuit. So V1 is Z2 divided by ZT multiplied by E. Okay, and in which circuit is this? This is basically here. Okay, so that is V1. I want to find out the V1, and this circuit has been transformed into this one. Okay, so this is basically E. So let me put their values here. So Z2 is how much? Z2 is 270.4 with an angle of 80.63 divided by the total voltage, and that is 21,540.66 with an angle of 68.19, and the total voltage here is how much? That is 120 volts with an angle of 0 degree. So 120 with an angle of 0 degrees. Okay, so now let me calculate it. So V1 will be here 270.4 multiplied by 120 divided by the 21,540.66. Okay, and here this is 80.63 plus 0 degree. These are the angles of the numerator terms, while subtracting 68.19 from it. Okay, so now let me calculate V1. Okay, so it would be 270.4 multiplied by 120. Okay, and divided by 21,540.66. Okay, so that is basically 112.92 and with an angle of 80.63 minus 68.19. So that would be 12.44 degrees, and this is basically in volts. So that is the value of V1. Okay, so V1 is calculated, and this V1 is basically this voltage. So now if I want to find out the V2, what I have to do, I have to transform my circuit into another version in which we will have again Z2. Here I will have this voltage source, and here let me call it Z3 and Z4. Okay, and here it will be, this voltage will be how much? This would be V2 as we have in our original circuit here. So that is V2, but that V2 is here, and this Z4 is equal to how much? Z4, let me use this Z4, and that is the combination of these two impedances. Okay, so 3.3 kilo and this capacitive reactance, so 3.3 kilo ohm and minus J 10 kilo, because we have a capacitor here. You may see here very clearly that this is a capacitor. So Z4 is this one. Okay, so now that is already in the rectangular form. Let me convert it into the polar form. So what I will have, 3300 minus 10,000. Okay, with the iota here. So that would be this one, and now complex this 3, and here I will have 10,530.4 with an angle of how much? With an angle of minus 71.73, minus 71.73. 73 degrees. This is again in ohm, so that is the omega. So that is the value of the Z4. Now what I have to do, I have to find out the value of Z4, and we can see that in our previous circuit and now in this circuit as well, the total impedance will remain same, because the value I will have Z1 plus Z2, which was in my previous circuit, is equal to the Z3 plus Z4, which is now here. Okay, so these are same, and these are basically the total impedance. So now in order to find out the voltage of V2, what I have to do, I have to write Z4 divided by ZT, and that is multiplied by my total voltage. Okay, putting their values and simplifying them. So 1053.04 multiplied by 120 divided by the total impedance, and that is 21,540.66. okay, and their angles are, the angle of it is minus 71.73. it has 0, while the denominator term, which will be subtracted. Okay, so the denominator term is this one, so that would be minus 68.19. so minus 68.19 it will be. So now calculating it, what I will have, 10,530.4 multiplied by 120, okay, and dividing it over 21,540.66. so I will have here 58.67. so V2 will be equal to 58.67, and the angle it has will be 71.73 plus 68.19. okay, so that would be 139.92, while the signs here are negative, so minus 139.92, and this is in volts, so that is the value of V2. okay, so we have calculated the values of V1 and V2 in our circuit by using the method which I have described, and transform my circuit into two more circuits and then analyzing them. Okay, so that's it for today, and I will see you with some more questions in our upcoming videos. Thank you so much and see you soon. Welcome back, guys. This is question number 18, and here we are asked that an electrical load has a power factor of 0.8 lagging. Okay, so it dissipates 8 kilowatt at a voltage of 200 volts. Calculate the impedance of this load in rectangular coordinates. Okay, so that is a very interesting question, and let me depict it by using a figure. So let me have a figure here in which we have this load. Okay, so what is basically the applied voltage here? The applied voltage here is, let me have it, 200 volts, and the power which dissipates across this load is 8 kilowatts. Okay, and the power factor associated with this load is 0.8 lagging. What we have to find out? We have to find out this Z naught. Let me call it Z naught. I have to find out this Z naught, and first of all let me also find out the current which it is getting out of this source. So in order to find it out, what are the quantities? I have this power factor here, so I know that the power factor is equal to the cos of theta. Okay, or in order to have it, I can also see that cos of theta is 0.8, or in order to find the value of theta, what is equal to cos inverse of 0.8, and what is it equal to? Let me calculate it. So cos inverse of 0.8, how much would it be? That is 36.87. so theta is 36.87 degrees. Okay, so that is the theta which I have. So now what else do I have? I have this power as well, that is the power dissipated, and that is basically the real power. So I know that the power is, real power is always equal to P equal to IV cos of theta, where this cos of theta is the power factor, okay, which I already know. So all the quantities here are known except this current. So in order to find the current here, what it will be, so it would be P divided by V cos of theta, or putting values here, what I will get, it would be 8000 divided by V, that is 200 multiplied by 0.8. okay, so these two will cancel out, and here this will be 40. So 40 divided by 0.8, so let me calculate it. 40 divided by 0.8, and how much it would be, this is now 50 amperes. okay, so the current, magnitude of the current is already known, which I have calculated right now. So now as the magnitude is already known, but there is another term here which is this lagging. okay, and I have previously told you, whenever this lagging term is used, that it will always be associated with the current. okay, always the current when leads, when this is leading, it means the current is leading. When the power factor is lagging, it means current is lagging. So here in power factor calculation, or in here always, there is always a relationship between voltage and current. okay, so now here, as voltage is leading and current is lagging, therefore in polar form, what it would be, it would be, if this is 200 and the angle with it is 0 degrees, so here this current would be how much, the magnitude it has is 50, while the angle it will have is this 36.87, which I have obtained from my power factor, and it would now be minus 38.87 degrees. okay, because of its lagging nature. And on the phasor diagram, you will very easily see that if this is the voltage which is now leading, so the current here will be here, which is lagging, and the angle it is making with it is theta, and this is what, this is the current. So that is the phasor diagram, and here this relationship is valid. okay, so from it I have calculated all the values. okay, so that is now a very simple circuit where I know the current, I know the voltage, and I want to find out this Z naught. So here the validity of Ohm's law also applies here. So according to Ohm's law, V is equal to I Z naught, or the value of Z naught is how much, that is V divided by I. okay, so now let me put these values. So Z naught is 200 0 degrees divided by the 50 with what, minus 36.87 degrees. okay, so that would be how much, that is now 4, and 4 ohm with an angle of 36.87 degrees. so that is the impedance of my load. But as we are asked to find out it in the rectangular form, because in that manner I would clearly know that what is the actual resistance and what are the reactive elements available in my load. So let me first do it in what, in my form here. So that is now 4, and the angle associated with it is 36.87. okay, so that is here, and the that is now the direct form, because now that is complex, and I already selected it to convert it into the rectangular form. So it would be 3.19. okay, so let me write it. So Z naught is now 3.19. okay, and with it the, yes, this is plus j 2.4, what, 2.4, yes, that is 2.4. so that is the impedance, where this is the real term which shows the resistance, while this is the reactance of my load. So, due to this reactance, the power factor is now lower than 1, and that is now 0.8. Okay. So, that is a very interesting question, by using which I can find out the impedances which are already connected with the machines, or in any household, or anywhere, whatever I want to find out. Okay. So, that's it for today, in which I have calculated the value of current, and from it I can also find out very useful information, just like the power consumption, energy consumptions, and so on. So, that's it for today, and I will see you with some more interesting questions like this one in our upcoming videos. Welcome back, guys. So, question number 20 of our book, in which we are asked to find the series element or elements that must be in the enclosed container, which is here. So, that is basically the enclosed container to satisfy the following conditions. Okay. So, conditions are basically mentioned here as part A and B. So, in first condition here is that the average power to the circuit is 300 watt. Okay. And in second part we are told that the circuit has a lagging power factor. Okay. So, here in order to approach this type of question, what we have to do, first of all, let me calculate this theta. Okay, because theta is one of the very important terms here in order to find the nature of the power factor. Okay. So, initially what we have given here, we are given the current, we are given the total voltage, and the resistor which is in series with this impedance, let me call it Z of x. Okay. So, we have to find out Z of x according to our conditions which are mentioned here. Okay. So, here the average power of a circuit is also given, that is 300 watt. So, I know that P is equal to the IV cos of theta. Okay, where this cos of theta, okay, this term here is the power factor. Okay. So, we have to find it out. So, in order to find it out, what we have to do, let me calculate this cos of theta, and cos of theta is P divided by IV. Okay, let me put their values here. So, P is the required average power is 300 watt. Okay, divided by the value of voltage which is 120. Okay, and the value of current is 3. So, that is now 300 divided by 360. Okay, and it would be equal to, let me calculate it. So, 300 divided by 360 is how much? That is 5 by 6 or 0.83. So, that is now 0.83. So, that is the value of cos of theta. The cos of theta is equal to 0.83. Okay, and the value of theta from this expression is cos inverse of 0.83. Okay, so let me calculate it again here. So, cos inverse of this is 0.83, that is how much? So, this is basically 33.9 degrees. 33.9 degrees, and that is this theta. Okay. So, the value of theta is 33.9, while according to this condition that the circuit has a lagging power factor, the power factor is already known, and that is 0.83, while when it will be lagging, so we will see that the voltage will lead while the current will be in lagging situation. So, therefore, I here will have the value 3 amperes, and the angle associated with it will be minus 33.9 degree, because of the same reason which I have mentioned in our previous video. Okay. So, that is the value of current. Now, in order to find out the value of this impedance, what I have to do, I have all the required values which should be here in order to find the total impedance, because the total voltage is known, total current is known. So, I can very easily find out the total impedance from this circuit as well. So, therefore, I have to make this circuit like here. this is the voltage source, while this one is the total impedance, and inside of it I have this resistor and this Z of X as well. Okay, so that is now 2 ohm. Okay, and the total overall impedance here is Z naught, which is basically 2 plus Z of X. Okay, so why am I transforming this circuit into this one? Because the current which is given here is the total current. Okay, that is the total current which this circuit is now getting. Okay, and that is also the total voltage which has been applied across the total impedance. Okay, so therefore we cannot separate out this 2 ohm resistor from the overall impedance. So therefore I want to find out the total impedance here, Z naught. Okay, so in order to find the Z naught by using the Ohm's law, this point will be somehow clear now again, because according to the Ohm's law, E is equal to I Z naught. Okay, or the value of Z naught, which is the total impedance connected with this voltage source, is E divided by I. Okay, let me put their values here. So it would be 120 degrees divided by the value of current is 3, and the angle with it is minus 33.9. Okay, so this Z naught will be equal to the 40 ohm and 0 plus 33.9 degrees, which will ultimately give me Z naught equal to the 40 ohm with an angle of 33.9 degrees. So that is the total impedance which we can see from this transformed version here as well. So that is, this is basically the total impedance, which is Z naught. Okay, so let me convert into the rectangular form, because from here what I have to find out, the actual thing which I have to find out here is this Z of X. So here, converting it into the rectangular form, let me use calculator here. So 40 and with an angle of 33.9, how much would it be? So that is 33.2. Okay, 33.2 and 22.3, 33.2 plus J 22.3. so that is the Z naught. So what this Z naught is equal to, I have previously told you guys that this Z naught is also equal to the 2 plus Zx. Okay, so Z naught is equal to 2 plus Z of X, and the quantity which I want to find out here is this Zx, which is now Z naught minus 2. So let me put these values here. So Zx is now 33.2 minus 2 plus J 22.3, or Z of X is equal to, this will be 31.2 plus J 22.3. Okay, so that is the required impedance. Okay, so now we can see that our whole circuit will be like this one. This is the resistance of 2 ohm, okay, which I had previously, and that is basically the voltage source, which is of 120 volts with a 0 degrees, and the current is of 3 amps and minus 33.9 degrees. Yes, 33.9 degrees. Okay, so this was basically here, what was here, we had this black box, and inside of it we had to find out the value of z of x. So now we can very clearly see here that the value of zx here is 31.2 plus j 22.3. So this basically 31.2 is the value of the resistor, while this 22.3 is the imaginary term. So therefore it basically shows us the reactive element, as the value of j here is positive. So that's why this one is the inductive reactance. Okay, so this is the whole impedance which will be inside this box. So therefore I can draw it like the first element here is this resistor, while the second element will be in series with it, and that is the inductor. Okay, so that is x of L, and that is now 22.3 ohm. Okay, while this is the resistor, and that is 31.2 ohm. Okay, so that is the end of our question, in which we have obtained this impedance from the conditions which are mentioned in our question here. Okay, that's it for today, and I will see you with some more interesting questions in our upcoming videos. Thank you so much, and I will see you soon. Welcome back, guys. So today we are going to learn another very important technique, and that is the current divider rule. Okay, so current divider rule is one of the most important rule in the circuit analysis. Okay, which is used to find the unknown currents. Okay, so in order to learn all the concepts behind the current divider rule, we are going to solve the question number 34 in our book, in which we are asked to find the values of current I1 and I2, okay, in a circuit where the total current or the source current has been given. So in order to solve this question, let me represent I1 with the red color, while this I2 with this green color. Okay, what we have to do, we have to apply the current divider rule to find out the currents here. So in order to do it, let me represent my circuit with another circuit in which the impedances are represented by these blocks. Okay, so this is block number 1, and similarly here we have another block, and let me call the impedance of it is Z2. Okay, so this is Z2, this is Z1, and what we have to do, we have to find out the current I1. I am representing it with the red color as I have mentioned it here, and similarly I want to find out the current I2. Okay, which I am going to solve by using the green color. So in order to find the value of I1, what I have to do, so by current divider law or current divider rule, what I have to do, I have to find out the value of current I1. So I have to take the ratio of the impedance which is in parallel with the impedance across which I want to find out the current. So the impedance across which I want to find the current here is the Z1, and the parallel impedance with it is Z2. Okay, so what I have to do for I1, I have to write here Z2, okay, and divide it over the summation of the impedances which are connected in parallel with each other. Okay, so here Z1 and Z2 are connected in parallel, so I am taking their summation and multiply it over the current, which is basically the source current, which is here. Okay, so that is the source current, and I have to multiply it with this one. Okay, so this is a very interesting equation, and that's why this is called the current divider rule. So here I have an issue that in this circuit I don't know the values of Z1 and Z2, while here I can find out the values by using the ratio of Z2 over Z1 plus Z2, while the value of I is already known, which is here. This is the value of I, which is already known. So in order to find the values of Z1 and Z2, let me see it here, that here we can see that this is Z1. Okay, if I can see here that, okay, so let me draw these values over here. So this is now, if I can see, so this is now Z2, while this one here, this is Z1. Okay, so here I can very easily see that the value of Z1 is how much, that is 22 ohm. As this is a real quantity, so I am going to write it like this one. Okay. Similarly, the value of Z2, we can see here that here two inductive reactances are connected in series with each other. So in series the impedances are added together. So I am going to write Z2 as XL1 plus XL2. Okay. So as these are the inductive reactances, therefore I must have to write J with them here as well. Now writing their values, what I will get, this will be J, the value of XL1 is 60 and the value of X2 is 20. So here Z2 will be equal to how much? This is now J 80. Okay, so that is J 80 ohm. So now I know the values here, so let me put these values over here. So I1 is now equal to the value of Z2 is J 80 divided by Z1 is 22 plus J 80 and multiply it with this current, total current, which is already given here, and that is 20 with an angle of 40 degrees. Okay, so now this one is the equation here which I have to solve, and for solving them, it is already known that here the mathematical operations involved are basically the multiplication and division, and for the multiplication and division the most feasible form for us is the polar form. Okay, so now I will also put the link of the video over here if you want to revise the concepts of the phasor. So I am putting the link over here. So now in order to solve it, what I have to do, converting them into the polar form. So here this J80 will be 80 with the 90 degrees. Okay, while this A22 plus J80 is how much? So let me calculate it. Okay, so 22 plus 80 with the iota. Okay, now converting it to the polar form, this one, and in polar form it would be 82.96. okay, so that is now 82.96, and the angle it has is how much? Angle is now here, so that is 74.62. 74.62 multiplied with the current, which is already in the polar form. So now let me solve it. So here I1 is here, so now writing the amplitudes here. So 80 multiplied by 20 divided by 82.96. okay, and the angles associated with them are 90 degrees plus 40 degrees. So these are basically the angles associated with the numerators, while the denominator angle will be subtracted from them, so it would be 74.62. okay, so now the value of I1 is how much? Let me calculate it. So 80 multiplied by 20 divided by 82.96, so it would be how much? That is 19.29. so 19.29 amperes. okay, and the angle it has is 90 plus 40 is 130. 130 minus 74.62, so 130 minus 74.62, how much would it be? It is now 55.38 degrees. okay, so that is the value of current which I had to find out here. So I have very easily find out the value of current I1 by using the current divider law here. okay, now in order to find the value of the current I2, let me use the green marker here. So in order to do it, what I have to do, let me write the formula for the current divider law. So I2 is now how much? So the I2 current is flowing through the impedance Z2, so therefore I have to take the value of Z1 which is in parallel with the Z2, so Z1 then divided over the summation of the impedances and multiply it with the total current. So the same values here. Now writing the values here. So the value of Z1 is how much? The value of Z1 is, we can see here that this is 22 ohm. So 22 and divided over Z1 plus Z2, which is already the same value. So I have already converted it into the polar form. So let me use the polar form here as well, and that is 82.96 with an angle of 74.62 and multiply it with the total current, which is 20 and 40 degrees. Okay, so this one is again here. So now let me calculate the value of I2 by using the same procedure which I have done previously. So this 22 is the real quantity, therefore the angle with it is now 0 degrees. Okay, so now multiplying the amplitudes. So 20 multiplied by 22 divided by 82.96. okay, and the angles with it are 0 plus 40 and minus 82.96 degrees. Okay, so let me calculate it. So I2 is how much? Let me calculate it. So it would be 22 multiplied by 20 divided by 82.96. so it would be how much? That is 5.3 amps. So this is now 5.3 amps, and the angle it has is, that is plus 40 and minus 82.96 is minus 42.96 degrees. Okay, so that is the value of current which I had to find out. So this is I2. So we have seen that by using the current divider law we have found out the values of I1 and I2, and you can also find the same values if you already know the input current, which is basically the source current, and all the impedances which are connected in parallel with each other. Okay, so that is the essence of this question, and I hope all the conceptual ambiguities are clear now. Okay, so thank you so much, and I will see you with some more questions in our upcoming videos. See you soon. Welcome back, guys. So this is now another question. This is basically the part B of question 34, in which again we are asked to find out the values of current I1 and I2, and here we can see that the total current is already known. Okay, so what we have to do, we have to apply the current divider rule which we had previously used. Okay, so now in order to do so, let me use the same procedure. First of all, let me represent this circuit with other circuit in which the impedances are represented by these blocks. Okay, so this is block 1 while this is block 2 here. Okay, so let me call it Z1 and this Z2, and here the source current is already known, which is this I, while the values of current, this is I1. Okay, so let me represent it with this red color, or doing it like this is the Z1 while this one is I2. Okay, so let me represent this one with the green color. Okay, and this is Z2. So now we can see that this is a circuit in which this is Z1 while this is Z2. So what we have to do in order to find the value of I1, I have seen that the value of I1 is basically equal to what? Okay, so let me write the formula. The value of I1 according to the current divider law is Z2 divided by Z1 plus Z2 multiplied by I, and this formula is only applicable if Z1 and Z2 are in parallel with each other. Okay, so again I don't know the value of Z1 and Z2 while the value of I is already known, and that is here. Okay, so here let me write their values. So in order to do so, let me first calculate the values of Z1 and Z2. So the value of Z1 is how much? We can see here that this is the inductive reactance, so therefore this is JXL. Okay, so now writing its value, what I will get here J4 ohm. Okay, so that is the value of Z1. In order to find the value of Z2, we can see that here the resistor and the capacitive reactance are connected in series with each other. So therefore, what I have to do, this will be R, and here I will have this X of C. So as these are connected in series, so therefore minus J will be added with this X of C, and here I have this Z2. So now putting their values, what I will get, so Z2 is equal to 12 minus J 6. Okay, so that is basically the value of Z2. Now in order to find the value of I1, what I have to do, let me put their values here. So the value of Z2 is 12 minus J6 dividing it over Z1 plus Z2. So the value of Z1 is already known, that is J4, while the value of Z2 is plus 12 minus J6. Okay, and multiply it with what I have to multiply it with, this 6 and 30 degrees, because of this value. Okay, so this value is already known, which is the source current. So let me solve it now. So in order to solve it, what I have to do, so this is now I1. So I1 is 12 minus J6 divided by, as these two, we can see that this one and this one, these are two the imaginary quantities, while this one is the real one. So imaginary quantities will be added together. So therefore here I will get 12 and plus J4 and minus J6 is equal to minus J2. Okay, multiply it with this 6, 30 degrees. Okay, so now again the operations involved here are basically the multiplication and division. So therefore for multiplication and division, again the polar form is the feasible one. So converting these rectangular forms into the polar form, what I have to do, so let me represent them here. So 12 and minus 6 with an iota. So this one is here, and representing it in the polar form, what I have to do, shift 2, okay, 3. So what I will get, I will get here 13.4. okay, so 13.4 with an angle of minus 26.5. so 13.4 with an angle of minus 26.56. okay, and dividing over this 12 minus J2, again this is the rectangular form. So let me convert it into the polar form. So this will be 12 minus 2 with an iota. So here this is 12 minus iota, again converting into the polar form, what I will get, 12.17. so 12.17, and the angle with it is minus 9.46. okay, so angle with it is minus 9.46, and multiplying it with 6 and 30 degrees. okay, similarly in order to solve it now, multiplying the amplitude, so 13.4 multiplied by 6 divided by 12.17, and the angles here are minus 26.56. okay, and this one is the positive, so adding it with the numerator term here. So these two are the numerators which are added together, while this one is the denominator, and the sign of it will be changed. So therefore it will be 9.46. okay, so this is I1. so the I1 is now equal to 13.4 multiplied by 6 divided by 12.17. okay, so it would be 6.6 amperes, while the angles it has are minus 26.56 and plus this is 39.46, because 30 and 9.46 are added. So I will get 39.46. so what I will get, okay, so that will be 12.9. so here I will get 12.9 degrees. so this is the value of current I1. which I have found out by using the current divider law. Okay, so in this circuit I have found out the value of I1. Now to find out the current I2, what I have to do, I will represent my calculations with this green color. So now in order to do so, what I have to do, the value of I2 is what? This is Z1 divided by Z1 plus Z2. Why Z1? It is basically explained in my previous video, so I will put a link over here so you can basically see what does it mean to write the Z1 in the numerator despite Z2. Okay, so now multiplying it with I, the total current, now putting values here. So the value of I2 is, now the value of Z1 is how much? Z1 is J4. Okay, so the value of it is J4, and in polar form it will be 4 and 90 degrees. Okay, while the Z1 plus Z2 was previously converted into the polar form as well. Okay, so that is now 12.17 with an angle of minus 9.46. so 12.17 with an angle of minus 9.46. okay, and the total current here is how much? The total current here is 6, and the angle is 30 degrees. So 6 with an angle of 30 degrees. Okay, so these are all the values. So now let me solve them here, because all the values here are now in polar form. So it is now very easy for me to solve them by using the multiplication and division. So I2 is now 4 multiplied by 6 divided by 12.17. okay, and the angles here are 90 degrees plus 30 degrees plus 9.46. okay, so what I will get here, so the value of I2 will be equal to, that would be 4 multiplied by 6 divided by 12.17. okay, so this is now 1.97 amperes. okay, while the angles here are 90 plus 30 is how much? That is 120. so 120 plus 9.46 is 129.46 degrees. So that is the value of current I2 which I wanted to find out. Okay, so that's it for the part B of my question 34, and I have seen that how easy it is to find the values of the unknown currents if we know the source current and all the impedances which are connected in parallel with each other. Okay, so that's it for today, in which we have covered a very basic current divider rule, which is very important for you to understand in order to find the unknown currents. So that's it for today, and I will see you with some more important stuff in our upcoming video. Stay tuned, and if you have any question, please ask me in the comment section. Thank you so much, and see you soon.